the most bizarre objects in space that shouldn't exist. The universe is full of surprises, but some objects defy everything we thought we knew. Strange planets that orbit backwards, stars that spin faster than physics should allow, and mysterious interstellar visitors that appear from nowhere. These are the cosmic oddities that shouldn't exist. They challenge our understanding of how the universe works, push the limits of physics, and force scientists to ask questions they never imagined. So, let's dive into the most bizarre objects in space, exploring the weird, the impossible, and the utterly mind-bending mysteries of the cosmos. The most bizarre objects in space. Imagine a star so extreme that if it drifted halfway between the Earth and the Moon, it wouldn't burn cities or boil oceans. Instead, it would silently erase the magnetic data on every credit card on the planet. Hard drives would fail, electronics would glitch, and all of this would happen without the star ever touching Earth. That object exists, and it is not theoretical. It is real, observed, and documented. It is called a magnetar, and according to everything we understand about physics, it should not be able to exist at all. Magnetars are the most violent stars ever discovered. They are not just powerful, they are not just dense. They are objects where matter, energy, and magnetism are pushed so far beyond normal limits that familiar laws of physics begin to bend. These stars possess magnetic fields trillions of times stronger than Earth's, fields so intense they can distort atomic structures, tear apart their own surfaces, and send bursts of radiation across the galaxy strong enough to affect our planet from tens of thousands of light years away. The real mystery is not what magnetars do. The mystery is why they don't destroy themselves in the process. To understand why magnetars are such a problem for science, it helps to begin with neutron stars themselves, because even those are already extreme beyond imagination. A neutron star is formed when a massive star reaches the end of its life. After burning through its nuclear fuel, the star's core collapses under gravity. Protons and electrons are crushed together, forming neutrons, while the outer layers of the star explode outward in a supernova. What remains is a stellar core so dense that a single teaspoon of its material would weigh billions of tons on Earth. These objects are only about 20 kilometers across, yet they contain more mass than the Sun. Gravity on their surface is so intense that matter is locked into a rigid, crystalline crust, unlike anything found anywhere else in the universe. Even among neutron stars, magnetars are something else entirely. While normal neutron stars already have strong magnetic fields, magnetars push magnetism to an absurd extreme. Earth's magnetic field is weak enough that we barely notice it unless we're near the poles. A refrigerator magnet is stronger, but still trivial on a cosmic scale. A magnetar's magnetic field, by contrast, can reach 1 quadrillion Gauss. This is not simply stronger by a factor of 10 or 100. It is stronger by factors so large they defy intuitive comparison. At these strengths, magnetism becomes a dominant force shaping matter itself. This is where the first major problem appears. Magnetic fields store energy, and the stronger the field, the more energy it contains. At magnetar levels, that energy should be catastrophic. It should rip the star's crust apart, destabilize the internal structure, and overwhelm the forces holding the star together. In theory, a magnetic field this intense should cause the star to tear itself apart from the inside. According to classical models, the object should fracture, collapse, or violently shed mass. Yet magnetars remain stable, sometimes for thousands of years. This contradiction sits at the heart of why magnetars are so disturbing to astrophysicists. They exist in a regime where theory predicts failure, but nature continues anyway. The magnetic fields of magnetars do more than threaten the star itself. They fundamentally alter how matter behaves. Under such intense magnetism, atoms are no longer round or stable in the way we understand them. Electron clouds collapse and stretch along magnetic field lines, transforming atoms into elongated tube-like structures. Chemistry, as it functions on Earth, effectively stops working. Atoms bind differently, energy levels shift, and the familiar rules governing matter no longer apply. If a human body were exposed to this environment, even at a distance that avoided heat or radiation, the magnetic forces alone would disrupt atomic bonds. Matter would not burn or freeze. It would simply fail to hold together in any recognizable way. The path to discovering magnetars began almost by accident. In the late 1970s, satellites designed to monitor nuclear weapons tests started detecting sudden bursts of gamma radiation coming from deep space. These bursts were short, intense, and completely unexpected. At first, scientists assumed they were seeing gamma-ray bursts from distant galaxies, massive explosions marking the deaths of stars or the mergers of compact objects. But something didn't add up. Some of these sources were repeating. They were producing multiple bursts over time, which should not happen if the source was a one-time catastrophic explosion. As more data came in, it became clear that these repeating gamma-ray sources were something new. They were labeled soft gamma repeaters, objects that emitted bursts of high-energy radiation without destroying themselves. This alone was strange. In the 1990s, X-ray satellites provided even more detail. Astronomers observed slow-spinning neutron stars emitting enormous amounts of energy, far more than their rotation could explain. These objects did not behave like pulsars, which shine by converting rotational energy into radiation. They did not show signs of accreting material from companion stars. They were isolated, yet incredibly active. The breakthrough came when scientists proposed that these stars were powered not by spin or gravity, but by magnetism itself. In this model, the magnetic field was so strong that its gradual decay released vast amounts of energy. This energy cracked the star's crust, heated its surface, and drove powerful emissions of X-rays and gamma rays. In the mid-1990s, the term magnetar was introduced, and for the first time, the behavior of these strange objects began to make sense. Not because they were understood, but because they were finally named. What truly sets magnetars apart is how violently they release energy. One of their defining behaviors is something called a starquake. Neutron stars have a solid crust, a rigid lattice of ultra-dense matter. As a magnetar's magnetic field twists and evolves, it exerts enormous stress on this crust. Over time, the stress builds until the crust can no longer hold. When it breaks, it releases an immense amount of energy in a fraction of a second. This energy escapes as gamma rays and X-rays, producing some of the most powerful flashes ever observed in the universe. The most dramatic example of this occurred on December 27, 2004. A magnetar, known as SGR 1806-20, unleashed a flare so powerful that it momentarily became the brightest object ever detected outside our solar system. For a brief instant, it outshone everything else in the galaxy in high-energy radiation. Satellites designed to monitor cosmic explosions were overwhelmed. Detectors saturated. Instruments went offline. This magnetar was located about 50,000 light-years away, on the far side of the Milky Way. Yet its energy was strong enough to reach Earth with measurable effects. When the radiation from the flare arrived, it interacted with Earth's upper atmosphere. The ionosphere was disturbed, radio signals fluctuated, sensors recorded sudden changes in atmospheric ionization. This was not a theoretical simulation or a model. It was a real observed interaction between a distant star and our planet. Scientists later calculated that if a flare of this magnitude had occurred within a few light-years of Earth, it could have caused severe damage to the ozone layer. At closer distances, the biological consequences could have been catastrophic. This single event permanently changed how scientists think about the potential danger posed by nearby magnetars. The fact that magnetars can survive such violent outbursts only deepens the mystery. Why don't they tear themselves apart? Current research suggests that the answer lies in the exotic nature of neutron star interiors. Inside a magnetar, matter may exist in states that cannot be reproduced in any laboratory. Neutrons may form superfluids, protons may behave as superconductors, and magnetic fields may be locked into the star's core in complex structures that prevent immediate collapse. The star's immense gravity may also play a role, counterbalancing the outward pressure generated by the magnetic field. None of these explanations are fully confirmed. They are active areas of research, constantly refined as new data arrives. Magnetars are also rare. In a galaxy containing hundreds of billions of stars and millions of neutron stars, only a few dozen magnetars are known. Their rarity suggests that they form only under very specific conditions. Scientists believe magnetars are born from massive stars whose cores collapse while spinning extremely fast. This rapid rotation amplifies the magnetic field during collapse, producing a newborn neutron star with an exceptionally strong magnetic field. If the star spins too slowly, it becomes an ordinary neutron star. If it spins too fast or collapses too completely, it may form a black hole instead. Magnetars exist in a narrow window between these outcomes. One of the most important recent developments in magnetar research involves their connection to fast radio bursts. Fast radio bursts are brief, intense flashes of radio waves that last only milliseconds but release enormous amounts of energy. For years, their origin was unknown. Then, in 2020, a magnetar in our own galaxy produced a radio burst that closely matched the properties of fast radio bursts observed from distant galaxies. This was the first direct evidence linking magnetars to at least some fast radio bursts. While not all fast radio bursts come from magnetars, the connection has reshaped how scientists understand both phenomena. Despite decades of study, magnetars remain unpredictable. They can remain quiet for years, then suddenly erupt with devastating energy. Their spin rates can change unexpectedly. Their emissions vary in ways that challenge existing models. Each new observation forces scientists to revise their understanding of how extreme magnetic fields interact with matter. Magnetars are not anomalies to be ignored. They are data points that expose the limits of current physics. What makes magnetars so valuable to science is precisely what makes them so unsettling. They operate in conditions far beyond anything humans can create or control. They provide natural laboratories for studying matter at nuclear densities and magnetic fields at unimaginable strengths. They test theories of quantum mechanics, nuclear physics, and astrophysics all at once. They are evidence that nature can operate far beyond the boundaries we once believed were absolute, and that the universe still contains forces we are only beginning to understand. Blue stragglers, stars that refuse to age. In star clusters, time usually leaves visible marks. Stars form together, burn their fuel together, and slowly fade together. Astronomers rely on this shared aging process to read the history of the universe. When a group of stars is born at the same time, their brightness, color, and size follow predictable patterns. Older stars cool, redden, and move off the main sequence. Younger stars burn hotter and shine blue. This pattern is so reliable that entire branches of astronomy depend on it. Blue stragglers break that pattern completely. They appear in places where they do not belong. In clusters that are billions of years old, where every star should already be aging or dying, these stars stand out as bright, blue, and energetic. They look young in environments where youth should be impossible. They sit above the main sequence line in star cluster diagrams, shining hotter and stronger than stars that should have exhausted their fuel long ago. Their presence creates a direct conflict between observation and theory. If all stars in a cluster formed at the same time, then blue stragglers should not exist there at all. Yet they are not rare. They appear in globular clusters, open clusters, and even near the crowded cores of galaxies. Their behavior is consistent across environments, and their properties are measurable and repeatable. These are not errors in data or mistakes in observation. They are real stars that appear to have ignored the clock that governs stellar life. Astronomers first noticed blue stragglers in the 1950s while studying globular clusters. These clusters are among the oldest structures in the Milky Way, some more than 12 billion years old. When scientists plotted the stars in these clusters on a Hertzsprung-Russell diagram, the result should have shown a clear turn-off point where stars leave the main sequence. Instead, they found stars extending beyond that point, bluer and brighter than the rest. At first, This was confusing but not alarming. Early data was limited and instruments lacked precision. But as more clusters were studied, the same strange stars kept appearing. Different telescopes, different clusters. Same result: blue stars where only old stars should exist. By the 1960s and 1970s, blue stragglers were accepted as a genuine astrophysical problem. They could not be explained by normal stellar evolution. They were not new stars forming inside old clusters, since those environments lacked the gas needed to create stars. They were not foreground stars drifting into view, because their motion matched the clusters they lived in. They were not measurement errors, because their spectra confirmed their mass, temperature, and luminosity. They were stars that looked younger than their surroundings, without any clear reason why. In stellar physics, age is not guessed, it is calculated. Stars burn hydrogen in their cores, and the rate of that burning depends on mass. Heavy stars burn fast and die young. Light stars burn slowly and last for billions of years. In a cluster, the most massive stars leave the main sequence first. That creates a clear cutoff point that marks the cluster's age. Anything above that point should already be gone. Blue stragglers sit above that cutoff. Their brightness and color indicate masses higher than the cluster's turn-off mass. That means they should have burned through their hydrogen long ago. According to standard models, these stars should already be red giants, white dwarfs, or remnants of supernovae. Instead, they are still burning hydrogen as if time restarted for them. This directly violates the assumption that all stars in a cluster evolve independently. It also breaks the idea that stellar aging depends only on mass and composition. Blue stragglers behave like stars that somehow gained fresh fuel long after formation. The problem is that stars cannot simply refill their cores under normal conditions. The conflict is not subtle. If blue stragglers are treated as normal stars, they distort age estimates of clusters. They affect population models, chemical evolution calculations, and simulations of galactic history. Ignoring them is not an option because they are too bright and too numerous to dismiss. In some globular clusters, blue stragglers are concentrated near the center. In others, they appear spread out. Their distribution changes from cluster to cluster, suggesting that environment plays a role. Their masses are higher than average, but not extreme. Their rotation rates are sometimes faster than expected. Their chemical signatures occasionally show signs of mixing or unusual element ratios. None of this fits cleanly into standard stellar evolution theory. The deeper problem is that blue stragglers imply stars can alter their evolutionary path after formation. That idea challenges one of the core simplifications used in astrophysics. Stars are supposed to be predictable once their initial mass and composition are known. Blue stragglers are evidence that interactions can rewrite that script. This realization forced astronomers to look beyond single-star evolution and into the messy dynamics of crowded star systems. How scientists explain them. Two main explanations emerged as data improved. Both involve stars interacting directly with other stars, something that happens often in dense clusters where stars pass close to each other over millions of years. The first explanation is stellar mergers. In dense environments like globular cluster cores, stars can collide. These collisions are slow by cosmic standards, not explosive like car crashes, but gravitational encounters that allow two stars to spiral together and merge. When this happens, their hydrogen supplies combine. The result is a single star with more mass and fresh fuel in its core. This merged star appears younger because it now burns hydrogen again at a higher rate. Its position on the Hertzsprung-Russell diagram shifts upward and blueward, placing it exactly where blue stragglers are observed. Computer simulations show that merger products can remain stable for long periods, matching observed blue straggler lifetimes. Evidence for this comes from the environments where blue stragglers are most common. In clusters with high stellar densities, collisions are more likely. These clusters often show higher concentrations of blue stragglers near their centers, where interactions are strongest. This spatial pattern supports the merger hypothesis. The second explanation involves mass transfer in binary star systems. Many stars form in pairs. If two stars orbit each other closely, the more massive one evolves faster. As it ages and expands, it can begin transferring mass to its companion. That companion gains hydrogen-rich material, increasing its mass and effectively resetting its evolutionary clock. The donor star, meanwhile, loses mass and becomes faint or compact. The receiving star becomes hotter, brighter, and bluer. To an observer, it looks younger than it should. This process can occur without dramatic collisions and works even in less dense environments. Binary mass transfer explains blue stragglers found outside cluster cores, where collisions are less frequent. It also accounts for cases where blue stragglers show evidence of unseen companions, such as white dwarfs left behind after mass transfer ends. Both processes likely occur. The relative importance of each depends on the cluster's density, age, and structure. Some clusters favor mergers, others favor binaries. Some show evidence of both operating at the same time. Observational proof did not come easily. Blue stragglers are small, distant, and packed tightly among thousands of other stars. Ground-based telescopes struggled to separate them clearly. That changed with the launch of the Hubble Space Telescope. Hubble's high resolution allowed astronomers to isolate individual stars in dense cluster cores. For the first time, detailed color and brightness measurements of blue stragglers became possible. Studies confirmed that these stars were indeed more massive than the cluster average. Some showed rapid rotation, consistent with merger remnants. Others showed signs of binary companions, supporting the mass transfer model. Long-term monitoring revealed something else. Blue stragglers do not form all at once. They appear continuously over time. This means the processes creating them are ongoing, not relics of early cluster history. Clusters are not static systems. They are dynamic environments where stars interact, exchange mass, and alter each other's futures. Population studies across dozens of clusters strengthened this conclusion. Clusters with higher interaction rates produce more blue stragglers. Clusters with more binaries also show increased numbers. The correlation holds across different ages and metallicities, suggesting a universal mechanism rather than a special case. Spectroscopic studies added further detail. Some blue stragglers show unusual surface abundances, consistent with material pulled from deep inside another star. Others appear chemically normal but dynamically peculiar. This diversity indicates that blue stragglers are not a single phenomenon, but a category formed by multiple pathways. Modern simulations now include detailed gravitational interactions, stellar evolution, and binary physics. These models can reproduce observed blue straggler populations with increasing accuracy. They show how stars gain mass, how orbits change, and how merger remnants settle into stable configurations. Despite this progress, blue stragglers remain important because they expose the limits of simplified models. Any theory that treats stars as isolated objects fails in dense environments. Blue stragglers force astronomers to account for interactions, collisions, and mass exchange as fundamental drivers of stellar evolution. They also affect how cluster ages are measured. Ignoring blue stragglers can skew results. Accounting for them improves accuracy but adds complexity. This has consequences for studies of galaxy formation, since globular clusters are used as benchmarks for the early universe. Blue stragglers do not overturn stellar physics, but they complicate it. They show that stars are not always solitary, predictable objects. In crowded regions of space, stars influence one another in ways that can restart nuclear burning, reshape evolution, and create objects that look younger than their surroundings without violating physical laws. Their existence is no longer in doubt. Their mechanisms are increasingly well supported. What remains is refining the balance between collisions and binaries, understanding how environment shapes outcomes, and integrating these processes into broader models of stellar populations. Blue stragglers persist not because theory failed, but because reality is more interactive than early models assumed. Zombie stars, the supernovae that failed to kill their own stars. In astronomy, a supernova is supposed to be final. It is the moment a star ends its life, releasing so much energy that it briefly outshines an entire galaxy. The core collapses, the outer layers are blown away, and what remains is either a neutron star or a black hole. That is the rule. That is how stellar death has been taught, modeled and simulated for decades. Zombie stars break that rule. They are stars that go through a supernova-like explosion, but somehow survive it. The blast happens. The light curve spikes. The star ejects material into space. Telescopes record the event and label it a supernova. But when astronomers look back later, something is still there. The star's core has not collapsed completely. Nuclear burning resumes. The object remains active. These are not theoretical possibilities. They are observed events recorded by modern surveys. They are weak, incomplete explosions that leave behind a living stellar remnant where none should exist. This is why they are called zombie stars. They should be dead, but they are not. To understand why zombie stars are such a problem, it is necessary to understand what normally triggers a supernova. In massive stars, the core eventually fills with iron. Iron does not release energy when fused, so once iron builds up, the star loses its main energy source. Gravity takes over. The core collapses in a fraction of a second. Protons and electrons are crushed together into neutrons, and the sudden halt of collapse creates a shockwave that blows the star apart. This process is violent, fast, and catastrophic. The energy involved is enormous. Once it begins, there is no mechanism in standard physics to stop it halfway. Either the collapse happens and the star dies, or it does not happen at all. Zombie stars sit in the middle of this process. The collapse starts, energy is released, material is ejected, but the core does not fully give way. The explosion lacks the power to completely unbind the star. The result is an object that has gone through a failed death. In existing stellar evolution models, this outcome should be extremely rare or impossible. Simulations predict either a full supernova or no explosion at all. A partial explosion that leaves the star intact creates serious problems for those models. For most of the 20th century, astronomers did not know these objects existed. Supernovae were classified by their brightness, spectra, and decay rates. Anything that looked faint was assumed to be far away, obscured by dust, or poorly observed. That assumption began to fail in the early 2000s, when wide-field surveys became powerful enough to catch large numbers of supernova at very early stages. Astronomers started noticing a class of explosions that were far weaker than expected. These events released less energy, ejected less mass, and faded more quickly than normal supernovae. At first, these were dismissed as minor variations, but patterns began to appear. The same strange properties repeated across different galaxies, different environments, and different observing instruments. These were not observational errors. Something new was happening. Supernova 2008 HA, the event that changed everything. The turning point came in 2008 with an explosion known as Supernova 2008 HA. This event was detected in a nearby galaxy and immediately stood out as abnormal. It was one of the faintest supernova-like explosions ever recorded. Its energy output was roughly 1/100th of a typical supernova. The amount of material ejected was unusually small. At first, astronomers assumed this was a low-mass star producing a weak explosion, but follow-up observations complicated that explanation. The chemical signatures in the ejected material suggested incomplete nuclear burning. The explosion had started, but stopped before it could fully process the star's core. More importantly, later observations suggested that something was still present at the explosion site. The star had not vanished. Years after Supernova 2008 HA faded, astronomers used the Hubble Space Telescope to examine the exact location of the explosion. Instead of empty space, they detected a faint object consistent with a surviving stellar remnant. This was shocking. In a normal supernova, nothing resembling the original star remains visible. Either a compact remnant forms or the material disperses completely. In this case, the data suggested that the star's core had survived the explosion and continued to exist. This was the first strong observational evidence that some supernovae fail to fully destroy their stars. The leading explanation for zombie stars involves a type of explosion called a failed detonation. In certain stars, especially white dwarfs or low-mass massive stars, the conditions may trigger nuclear burning that does not propagate efficiently. Instead of a runaway explosion that tears the star apart, the burning front stalls. Energy is released, but not enough to overcome the star's gravitational binding. Material is ejected, but the core remains intact. In some models, the explosion actually pushes material outward and then allows some of it to fall back onto the core. This fallback further stabilizes the remnant, allowing it to continue nuclear burning. The result is a star that has been partially unmade and then stitched back together by gravity. One of the most disturbing aspects of zombie stars is that they do not simply survive in a dormant state. Many appear to continue nuclear reactions after the explosion. This suggests that the core retains enough pressure and temperature to keep fusion going. In standard theory, the conditions that trigger a supernova should also end fusion permanently. The fact that fusion can restart or continue implies that the explosion did not disrupt the core structure as expected. This challenges assumptions about how energy moves through stellar interiors during collapse and explosion. It suggests that energy transport, turbulence, and magnetic effects may play a larger role than previously thought. A new class of stellar explosion. As more events like supernova 2008 HA were discovered, astronomers realized they were dealing with a distinct category of explosion. These events were grouped into a class often called Type IAX supernovae. Type IAX explosions share several defining features. They are less energetic than normal supernovae. They eject less mass. They show evidence of incomplete burning, and in some cases, they leave behind a surviving remnant. This was not a minor adjustment to existing categories. It required the creation of an entirely new classification. Once astronomers knew what to look for, they began finding zombie stars more frequently. Surveys showed that Type IAX events make up a significant fraction of all observed supernova-like explosions in some galaxies. This raised an uncomfortable question. If these events are relatively common, why were they missed for so long? The answer lies in observational bias. Zombie star explosions are faint. They fade quickly. Older surveys were not sensitive enough to detect them reliably. Modern telescopes changed that. Supernova models are foundational to astrophysics. They explain how elements are formed, how galaxies evolve, and how compact objects are created. Zombie stars undermine several of these assumptions at once. If stars can partially explode and survive, then the link between stellar mass and final fate is less clear than believed. The amount of energy released in a supernova may vary far more than models predict. The production of heavy elements may also differ. This affects everything from chemical evolution models to estimates of neutron star and black hole populations. Zombie star explosions leave behind chemical signatures that differ from normal supernovae. The ejected material shows unusual ratios of elements like iron, nickel, and intermediate mass elements. These patterns indicate that nuclear burning stopped early. The star did not reach the conditions needed to fully synthesize heavy elements. This has consequences for how galaxies build up their elemental content over time. If zombie stars are common, then existing models of chemical enrichment may need adjustment. Some zombie stars are thought to originate from white dwarfs in binary systems. In these scenarios, a white dwarf pulls material from a companion star. As it gains mass, nuclear burning ignites. But instead of a full thermonuclear explosion that destroys the white dwarf, the burning stalls. The white dwarf partially explodes, ejects material, and survives. It may even continue accreting matter and repeat the process later. This introduces the possibility of stars that explode more than once. If a zombie star survives its first explosion, it raises the possibility of future outbursts. The remnant may be unstable, with altered composition and structure. Over time, it could explode again or collapse later. This creates a new category of long-term stellar evolution that has barely been explored. These objects may undergo multiple violent episodes before finally dying. Detecting zombie stars is difficult. Their explosions are faint. Their remnants are dim. Confirming survival requires precise follow-up observations years after the event. The James Webb Space Telescope and next-generation ground-based observatories are expected to play a key role in identifying more of these objects. By detecting infrared signatures and faint remnants, astronomers hope to determine how common zombie stars really are. Zombie stars are not just a curiosity. They expose weaknesses in current simulations. They reveal gaps in understanding of nuclear physics under extreme conditions. They show that stellar death is not always final. Most importantly, they remind astronomers that even the most established processes in astrophysics can behave in unexpected ways when pushed to their limits. The existence of zombie stars is not an interpretation, it is an observation. Stars have been seen to partially explode and survive. The challenge now is to explain how, but that explanation does not yet exist in full, and that leads us to black holes. Black holes that break physics. Supermassive black holes are objects with masses millions to billions of times greater than the Sun, and in the modern universe they are found at the centers of nearly all large galaxies, including the Milky Way. Their existence in today's universe is no longer surprising, because astronomers have had billions of years of cosmic time to explain how smaller black holes could slowly grow by feeding on surrounding gas, dust and stars, merging with other black holes along the way. The problem begins when these same objects are observed in the very early universe, at a time when the cosmos itself was still extremely young and had not existed long enough for known growth processes to operate. According to standard cosmology, the universe is about 13.8 billion years old, and when astronomers look back to the first billion years after the Big Bang, they are looking at an era when galaxies were only beginning to form, stars were just starting to shine, and the large-scale structures of the universe were still assembling. In this environment, the presence of fully formed supermassive black holes presents a serious conflict with established physical models. The issue is not that black holes exist early on, because stellar mass black holes can form quickly when massive stars collapse. The issue is scale. A black hole with a mass of 10 or 20 times that of the Sun can form in a few million years, which is fast on cosmic timescales. However, turning such an object into a black hole with a mass of 1 billion suns requires a long and steady supply of material, because there are strict limits on how fast black holes can grow. These limits are imposed by radiation pressure. As matter falls into a black hole, it heats up and emits enormous amounts of radiation. This radiation pushes outward and counteracts the inflow of new material. Once this balance is reached, the black hole enters what is known as Eddington limited accretion, which caps the growth rate. Under ideal conditions, even if a black hole feeds continuously without interruption, growing at the fastest rate allowed by physics, it would still take hundreds of millions to over 1 billion years to reach supermassive size starting from a stellar mass seed. This growth timescale creates a direct contradiction when astronomers observe supermassive black holes less than 800 million years after the Big Bang. At that age, the universe had not existed long enough to allow a small black hole to grow into a 1 billion solar mass object through standard accretion. Even if the first stars formed extremely early and produced black hole seeds almost immediately, there is still a shortage of time. This is not a minor discrepancy that can be fixed with small adjustments. The numbers simply do not work when using conventional models of black hole growth. Another issue lies in the environment of the early universe itself. The first galaxies were chaotic, small, and unstable, with violent star formation and frequent mergers. While mergers can help black holes grow, They also disrupt gas flows and can shut down accretion for long periods. In addition, the early universe was filled with intense radiation from young stars, which ionized gas and made it harder for matter to cool and fall into gravitational wells. This hostile environment should slow black hole growth, not accelerate it. Yet observations show black holes that are already fully developed and actively accreting, emitting enormous amounts of energy as quasars, at a time when theory predicts they should barely exist. The problem becomes even more severe when considering the luminosity of these early black holes. Many of them are observed as quasars, meaning they are not only massive but also feeding at near maximum rates. A quasar powered by a supermassive black hole releases more energy than an entire galaxy of stars, and maintaining that output requires a stable and sustained supply of infalling material. This implies that these black holes are not only large but embedded in well-organized environments capable of delivering gas efficiently. Such environments are difficult to reconcile with the turbulent conditions expected in the first few 100 million years of cosmic history. Standard cosmological simulations struggle to produce these objects without invoking extreme and often unrealistic assumptions. To force the models to work, researchers must assume either uninterrupted, perfectly efficient accretion for hundreds of millions of years, or initial black hole seeds that are already far more massive than any known stellar remnant. Both approaches push current understanding beyond what is supported by observational evidence from later cosmic times. As a result, early supermassive black holes are not just unusual objects. They represent a fundamental stress test for theories of gravity, star formation, and cosmic evolution. The tension between observation and theory has grown steadily as telescopes have improved. Earlier detections could be dismissed as rare anomalies or measurement errors, but the growing number of early quasars has eliminated that possibility. These objects are not one-off exceptions. They form a population, and that population exists precisely where models say it should not. This is why early supermassive black holes are often described as breaking physics, not because the laws of physics fail outright, but because current frameworks built upon those laws cannot account for what is being observed. The discovery of supermassive black holes. The discovery of supermassive black holes in the early universe began with the detection of distant quasars, objects so bright that they can be seen across vast stretches of space and time. Quasars were first identified in the 1960s as strange radio sources with enormous redshifts, indicating that they were extremely far away. Over time, astronomers realized that quasars are powered by supermassive black holes actively accreting matter, with the surrounding accretion disk converting gravitational energy into light. As surveys expanded and instruments improved, researchers began pushing deeper into the early universe, searching for quasars at higher and higher redshifts, which correspond to earlier cosmic epochs. A major breakthrough came with the identification of quasars at redshifts greater than 6, meaning they existed when the universe was less than 1 billion years old. Each new detection raised the same question: how did such a massive object form so quickly? As redshift records were broken, with quasars detected at redshifts above 7, the problem became impossible to ignore. These objects were not marginally massive. Some had black hole masses exceeding 1 billion suns, measured through the motion of gas in their vicinity and the properties of their emitted light. The uncertainties in these measurements were not large enough to erase the discrepancy. Even at the lower end of the estimates, the black holes were still far too massive to be explained by standard growth scenarios. The discovery process itself relies on careful analysis of light that has traveled for more than 13 billion years. Astronomers use spectroscopy to measure redshift, determining how much the expansion of the universe has stretched the light. From this information, they infer distance and age. The brightness and spectral features of the quasar reveal the mass of the black hole and the rate at which it is accreting matter. Multiple independent methods are used to cross-check these results, reducing the chance that systematic errors could explain the findings. Over time, consistency across different observations has strengthened confidence that these early supermassive black holes are real and not artifacts of measurement. Faced with this evidence, scientists have proposed several explanations, each attempting to bypass the time problem in a different way. One major idea is the direct collapse black hole model. In this scenario, instead of forming from the death of a single star, a black hole forms directly from the collapse of a massive cloud of gas. If certain conditions are met, such as low levels of heavy elements and intense radiation that prevents normal star formation, a gas cloud could collapse almost entirely into a black hole with a mass of tens of thousands or even hundreds of thousands of suns. Starting from such a large seed dramatically reduces the growth time needed to reach supermassive scales. Direct collapse models are appealing because they eliminate the slow, early stages of growth, but they require very specific conditions that may be rare. The gas must avoid fragmenting into stars, which normally happens when cooling processes are efficient. To prevent this, the cloud must be exposed to strong ultraviolet radiation that suppresses molecular hydrogen formation, keeping the gas hot and smooth. Whether such environments were common enough in the early universe to explain the observed number of quasars remains an open question. Simulations show that direct collapse is possible, but it is not yet clear if it can account for the full population of early supermassive black holes. Another line of explanation focuses on exotic early universe conditions that allow black holes to grow faster than normally expected. Some models suggest that early accretion may have exceeded the Eddington limit for extended periods. If radiation escapes in certain directions, or if the structure of the accretion flow is highly irregular, it may be possible for a black hole to consume matter at rates higher than standard theory predicts. This kind of super Eddington accretion has been observed on small scales in certain systems, but sustaining it for hundreds of millions of years on the scale required for early supermassive black holes is still highly uncertain. There are also theories that modify the initial mass function of the first stars, known as population third stars. These stars are thought to have been extremely massive, possibly hundreds of times the mass of the Sun. If such stars collapse directly into black holes without losing much mass, they could produce relatively large seeds. Even so, calculations show that this alone is usually insufficient to explain billion solar mass black holes by redshift 7 without invoking additional growth-enhancing mechanisms. The models often require nearly perfect conditions, with uninterrupted accretion and frequent mergers, pushing them to the edge of plausibility. Observational progress has accelerated with the launch of the James Webb Space Telescope. Webb's infrared sensitivity allows it to peer deeper into cosmic history than any previous telescope, detecting faint galaxies and quasars that were invisible before. Early data from Webb has already revealed a surprising abundance of massive galaxies and active black holes at very high redshifts, reinforcing the idea that structure formation in the early universe was more rapid and efficient than previously thought. These observations do not yet provide definitive answers, but they confirm that the problem is not limited to a handful of extreme objects. Webb's spectroscopic capabilities also allow astronomers to study the environments around early supermassive black holes in unprecedented detail. By analyzing the chemical composition, temperature, and motion of surrounding gas, researchers can infer how these black holes are feeding and how their host galaxies are evolving. Early results suggest that some of these systems are surprisingly mature, with organized gas flows and significant metal enrichment, indicating multiple generations of star formation have already occurred. This maturity adds another layer of complexity, as it implies rapid galaxy evolution alongside rapid black hole growth. Future observations aim to push even further back in time, searching for the earliest black hole seeds and the transition points where small objects became supermassive. Planned surveys with Webb and upcoming ground-based observatories will expand the sample size and reduce uncertainties, allowing scientists to test competing models more rigorously. If direct collapse black holes are common, their signatures should appear in these datasets. If super Eddington accretion dominates, evidence of extreme radiation patterns and unusual accretion structures should emerge. At present, no single explanation has solved the problem. Each proposed mechanism addresses part of the puzzle, but leaves other aspects unresolved. What is clear is that supermassive black holes in the early universe are not peripheral curiosities. They sit at the center of some of the most important questions in cosmology, forcing researchers to re-examine assumptions about how quickly matter can organize, collapse, and grow under the influence of gravity. The continued discovery of these objects ensures that this tension between theory and observation will remain one of the most active and challenging areas of modern astrophysics. The discovery of rogue black holes. Rogue black holes are some of the strangest objects ever confirmed in our galaxy because they exist without the one thing we expect every black hole to have: a visible home. For decades, astronomers believed black holes were always tied to something obvious. They were thought to sit in the center of galaxies, or feed off nearby stars in bright, violent binary systems. In those cases, you could see the damage. You could see gas heating up, glowing in X-rays, spiraling into darkness. Rogue black holes break that expectation completely. They wander alone through space, silent and invisible, carrying immense gravity with no light, no warning, and no clear sign they are even there. The reason rogue black holes shouldn't exist is not because they violate gravity or relativity, but because they violate how astronomers learn to find things. Almost everything we know in space is discovered through light. Stars shine, gas clouds glow, explosions flash across telescopes. Even most black holes announce themselves by tearing matter apart. Rogue black holes do none of that. They don't orbit a visible star. They don't pull in gas. They don't emit radiation. They drift through the galaxy like ghosts, obeying the laws of physics while completely hiding from the tools designed to study the universe. To understand why that is such a problem, it helps to understand how black holes usually form. When a massive star reaches the end of its life, it collapses under its own weight. The core falls inward, the outer layers rebound, and a supernova explodes. In many cases, the collapse leaves behind a neutron star. In the most extreme cases, the core collapses further and becomes a black hole. This process almost always happens inside a star system. Massive stars rarely form alone. They are born in clusters, surrounded by other stars, bound by gravity. When one of them dies, the black hole it leaves behind is expected to remain where the star was, still tied to its stellar neighbors. But supernovae are not gentle events. They are violent, uneven, chaotic explosions. If the blast is slightly lopsided, the newly formed black hole can receive a powerful kick. This kick can be strong enough to eject the black hole from its original system, sending it flying through the galaxy at hundreds of kilometers per second. Once that happens, the black hole becomes a wanderer. It no longer has a companion star to feed on. It no longer lights up in X-rays. It becomes effectively invisible. For a long time, this idea existed only in theory. Astronomers suspected rogue black holes should be out there, but suspicion is not evidence. The problem was simple and brutal. If an object emits no light, how do you find it in a universe that is mostly empty? You cannot point a telescope at darkness and hope something appears. For decades, rogue black holes remained an idea trapped on paper, impossible to confirm. The breakthrough came from a method that does not rely on light at all, but on gravity. Gravity does not care whether an object shines. Gravity bends space, and when space bends, light passing through it bends too. This effect is called gravitational lensing. When a massive object passes between Earth and a distant star, it can act like a lens, briefly magnifying the background star's light. The star appears to brighten, not because it changes, but because gravity is bending the light toward us. In the early 1990s, astronomers began using a more specific version of this effect called gravitational microlensing. Instead of creating dramatic arcs or rings, microlensing produces subtle changes in brightness. A background star brightens smoothly, then fades back to normal as the foreground object moves on. The shape and duration of this brightening curve reveal information about the mass of the invisible object doing the lensing. Most microlensing events are caused by ordinary stars. Some are caused by planets, but in rare cases the lensing lasts much longer than expected. Instead of days or weeks, the brightening can last months or even years. Long events suggest something very massive is passing in front of the star, something that emits no light of its own. This is where rogue black holes finally stepped out of theory and into observation. One of the most important confirmed cases came from years of careful data collection, combined with follow-up observations from space telescopes. Astronomers noticed a microlensing event that lasted far longer than any planet or normal star could explain. The background star's position also shifted slightly in the sky, a subtle wobble caused by the extreme gravity of the unseen object. This shift, called astrometric microlensing, provided the missing piece. By measuring both the brightness change and the positional shift, scientists could calculate the mass of the lens directly. The result was unmistakable. The object had several times the mass of the Sun. It emitted no detectable light. It was not part of a binary system. It was not surrounded by glowing gas. The only explanation left was a solitary black hole drifting through space. For the first time, astronomers had detected an isolated stellar mass black hole with no visible companion. A true rogue. This discovery changed how scientists think about the population of black holes in the Milky Way. Until then, estimates were based mostly on the small number of black holes found in binary systems. But those systems are easy to see precisely because they are loud. They glow, flare, and scream in radiation. Rogue black holes are quiet. If even one could be found through microlensing, it suggested there could be millions more hidden in the galaxy, completely undetected. That realization introduced a new and unsettling idea. The Milky Way may be filled with invisible heavy objects passing silently between stars, crossing spiral arms, drifting through regions where planets and solar systems exist. Most of the time, nothing happens. Space is vast, the distances are enormous, but the danger is not zero. A rogue black hole does not need to collide with something to cause damage. Its gravity alone is enough. If one were to pass close to a star system, it could disturb planetary orbits. It could pull comets out of deep storage regions. It could destabilize long-term gravitational balances that took billions of years to settle. If it passed close enough to a star, it could strip material away, briefly lighting up and announcing its presence far too late. The reason rogue black holes are considered dangerous is not because they are hunting planets, but because they are unpredictable. They cannot be tracked easily. They do not send advanced signals. They do not glow as they approach. They reveal themselves only through their effects, and those effects happen after the fact. Astronomers have tried to estimate how close the nearest rogue black hole might be. The numbers are uncertain, but models suggest there could be one within a few light years of the Sun. That distance sounds large, but in cosmic terms, it is a close neighbor. Even so, there is no immediate threat. Space is still mostly empty. The odds of a close encounter remain extremely small, but the existence of rogue black holes forces scientists to accept something uncomfortable. Our galaxy is not only filled with stars and planets, it is also filled with massive objects we cannot see, moving silently through the dark. Finding more rogue black holes is now a major goal of modern astronomy. New surveys are scanning millions of stars, watching for the telltale brightening curves of microlensing events. Space telescopes provide the precision needed to detect tiny positional shifts. Each new detection improves estimates of how many rogue black holes exist and how they move through the galaxy. These objects also provide a rare chance to test gravity itself. Because rogue black holes are isolated, their gravitational effects are cleaner and easier to model. They act like pure masses moving through space, unpolluted by glowing disks or violent interactions. Studying how they bend light helps refine measurements of mass, distance, and motion, and checks predictions made by general relativity in regimes that cannot be tested on Earth. There is also a deeper implication. Rogue black holes may carry information about how stars die. The number of wandering black holes, their masses and their speeds can reveal how asymmetric supernova explosions really are. A large population of fast-moving rogues would suggest that stellar deaths are far messier than once thought. A smaller, slower population would point to more symmetric collapses. Either outcome reshapes models of stellar evolution. Despite their name, rogue black holes are not rebels breaking the laws of physics. They follow gravity perfectly. What they break are expectations. They expose the limits of observation-based astronomy and force scientists to rely on indirect evidence, patience, and statistical certainty. They remind us that the universe does not need to be visible to be real. Somewhere in the Milky Way right now, a black hole with the mass of several suns is drifting through interstellar space. It has no companion. It emits no light. It leaves no trail. It bends space as it moves, quietly reshaping the paths of photons that cross its invisible influence. If it passes in front of a distant star, the star will briefly brighten, and for a moment, gravity will reveal what light cannot. By the time astronomers realized what they were looking at, the object was already leaving. It had slipped into the solar system quietly, without warning, without ceremony, and without behaving the way anything familiar ever had. It did not announce itself with a bright tail. It did not flare, or glow, or leave behind dust the way comets usually do. It arrived fast, cut through the inner solar system on a strange path, and then accelerated as it left, as if something unseen had given it a final push. That was the moment when scientists understood they were no longer dealing with a normal asteroid, a normal comet, or even a normal mystery. This was something else entirely, something that came from beyond the sun's domain, something that did not seem to follow the rules of solid objects moving through space. Oumuamua. The interstellar object that started a war in astronomy. The solar system is not an open door. It is more like a fenced yard with gravity acting as the gatekeeper. Objects can enter, but most of what we see has been here since the beginning. Asteroids, comets, planets, moons, all form from the same cloud of gas and dust that collapsed billions of years ago. Occasionally, long-period comets drift in from the far edges, but even those are still locals, loosely bound by the sun's pull. An object from another star system is different. It carries a history written somewhere else, shaped by another star, another disk of debris, another chain of violent events. For decades, scientists expected interstellar visitors to exist, but none had ever been confirmed. They were an idea on paper, not something you could point a telescope at. That changed in October 2017, when a telescope in Hawaii picked up a faint, fast-moving dot against the background of stars. At first, it looked ordinary enough. Another near-Earth object, another small body passing through the inner solar system. These things are tracked all the time, logged, named, and then mostly forgotten. But as more data came in, the object's path began to stand out. Its trajectory was not bound to the sun. It was not looping in from the outer solar system and swinging back out again. It was moving too fast. Its orbit was hyperbolic, meaning it had more than enough speed to escape the sun's gravity entirely. This object was not visiting. It was passing through. The discovery came from the Pan-STARRS telescope, a system designed to scan the sky night after night, watching for anything that moves. Pan-STARRS was built to protect Earth by finding asteroids that might pose a threat, not to rewrite astronomy textbooks. When the data was reviewed, astronomers quickly realized they were seeing the first confirmed interstellar object ever detected. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was a poetic name for something that immediately caused confusion, disagreement, and tension within the scientific community. The shock did not come from where Oumuamua came from. That part made sense. What shocked scientists was how it behaved once it was here. As it passed close to the sun, astronomers expected it to act like a comet. Comets are dirty snowballs. When they heat up, ice turns to gas, dragging dust along with it and creating a glowing cloud called a coma and a long tail that points away from the sun. This process also causes a small push, a kind of natural rocket effect that slightly changes the comet's speed. Oumuamua showed the push. Its motion changed in a measurable way as it moved away from the sun. But it did not show the coma. No gas cloud, no dust tail, no visible signs of outgassing at all. That combination should not happen. If an object accelerates without gravity being the cause, something must be pushing it. In space, that something is usually gas escaping from ice. But telescopes saw nothing escaping. Infrared observations showed no dust. Optical telescopes saw no tail. Radio telescopes heard nothing. The object was solid, dark, and silent, yet it was gaining speed. That alone was enough to spark arguments, but the strangeness did not stop there. As astronomers tracked Oumuamua's brightness over time, they noticed dramatic changes. It brightened and dimmed in a regular pattern, far more extreme than most asteroids or comets. The only way to explain that variation was shape. Oumuamua was not round. It was either extremely long and thin, like a cigar, or flat and wide, like a pancake. Both shapes were unlike anything ever seen naturally in the solar system. Typical asteroids are rough, lumpy, and irregular, but they do not stretch to such extremes. Oumuamua's brightness changes suggested a length many times greater than its width, or a flat disk tumbling through space. Either option raised new questions. How does such a shape form? How does it survive travel between stars without breaking apart? As weeks passed, the object moved farther away, growing fainter and harder to observe. Scientists had only a short window to collect data before it disappeared into the darkness. That urgency pushed researchers to analyze every photon, every data point, every possible explanation. Papers were written quickly, models were built, assumptions were challenged, and soon the calm surface of astronomy cracked into open disagreement. One camp argued that Oumuamua was a comet, just an unusual one. They suggested that it was made of exotic ice, something that does not produce dust or a visible tail when it sublimates. Hydrogen ice was proposed, a fragile form of frozen hydrogen that could evaporate without leaving much trace. Nitrogen ice was also suggested, similar to the surface of Pluto, where frozen nitrogen can sublimate directly into gas. These ideas could explain the acceleration without visible debris, but they came with problems. Hydrogen ice would be extremely fragile, likely to break apart long before reaching another star system. Nitrogen ice would require specific formation conditions and would still raise questions about how the object survived its journey. Another group focused on radiation pressure, the gentle push of sunlight itself. Light carries momentum, and if an object is thin enough, sunlight can push it measurably. This idea works for solar sails, thin sheets designed by humans to move spacecraft using sunlight. If Oumuamua were flat and thin, radiation pressure could explain its acceleration without gas. That explanation fit the data surprisingly well, but it introduced a new issue. What natural process creates a thin, sheet-like object hundreds of meters across? No known mechanism easily produces such shapes, especially one strong enough to survive interstellar space. There was no chance to observe it again, no chance to send a probe, no chance to resolve the arguments with new data. Oumuamua became a ghost, a single fleeting encounter that left behind more questions than answers. That scarcity of data intensified the conflict. With limited observations, scientists had to rely on models and assumptions, and different assumptions led to very different conclusions. The tension reached a breaking point when some researchers suggested a more controversial idea. They argued that Oumuamua could be artificial in origin, possibly debris from an alien technology, such as a broken light sail. This idea did not come from fringe voices, but from established scientists, which made the reaction stronger. Many astronomers pushed back hard, insisting that extraordinary claims require extraordinary evidence, and that natural explanations had not been exhausted. The debate spilled out of academic journals and into public discussions, media headlines, and conferences. Oumuamua was no longer just a strange object. It had become a symbol of how science handles the unknown. Behind the noise, serious work continued. Researchers re-examined the acceleration data, refining measurements and ruling out errors. They looked for any trace of gas using powerful telescopes and found none. They modeled different ice compositions and tested how they would behave under sunlight. They studied how objects might be stretched or flattened during close encounters with stars or planets before being ejected into space. Each study narrowed some possibilities and opened others. None provided a complete answer. One of the most important outcomes of Oumuamua's visit had nothing to do with what it was made of. It changed how astronomers think about interstellar objects as a population. Before 2017, interstellar visitors were hypothetical. After Oumuamua, they became real, and their estimated numbers increased dramatically. The fact that pan-stars found one by chance suggested that such objects might be common, passing through planetary systems all the time, unnoticed because they are small and fast. This realization led to new efforts to improve detection systems, to scan the sky more frequently, and to catch future visitors earlier. As attention turned to the future, another interstellar object appeared. In 2019, astronomers discovered 2Y/Borisov, a clearly active interstellar comet with a visible tail and familiar behavior. Borisov looked like what scientists had expected interstellar objects to be like all along. That contrast made Oumuamua even more puzzling. If Borisov was normal, why was Oumuamua so strange? Were there different classes of interstellar objects shaped by different environments and histories? Or was Oumuamua an extreme outlier, a rare case that happened to pass close enough to be seen? The comparison deepened the mystery rather than resolving it. Borisov followed the rules. Oumuamua broke them. The idea that interstellar space contains a wide variety of objects, some familiar and some deeply alien in behavior, began to take hold. That idea pushed astronomers to think beyond solar system biases. Objects formed around other stars may not look or act like the ones we know. Their materials, structures, and histories could be shaped by conditions we have never observed directly. This shift in thinking fed back into the debate over Oumuamua's solid nature. If it was solid, why did it behave like something that was not? If it was shedding material, why could none be detected? Some researchers proposed that the object was porous, more like a loosely bound aggregate than a solid rock, allowing gas to escape in unusual ways. Others suggested surface layers that trapped gas until it escaped in bursts too subtle to observe. Each idea tried to reconcile solidity with acceleration, structure with silence. The arguments played out in peer-reviewed journals, with papers responding to papers, models answering models. This was not a quiet academic disagreement. It was intense, sometimes sharp, driven by the fact that Oumuamua challenged assumptions that had gone untested for decades. The object forced astronomers to confront the limits of observation. You can only learn so much from a brief encounter with a fast-moving target. Beyond that, uncertainty takes over. Out of this uncertainty came change. Space agencies and research groups began discussing missions designed specifically to intercept interstellar objects. Concepts were proposed for fast spacecraft that could launch on short notice, chasing visitors like Oumuamua before they escape. Telescope surveys were upgraded and expanded. The Vera Rubin Observatory, designed to scan the entire sky repeatedly, became a key part of this new strategy. The goal was simple. Next time, do not miss the chance. Oumuamua's legacy is not a clear answer, but a shift in priorities. It exposed how unprepared astronomy was for something it had long assumed would one day appear. It showed how quickly confidence can turn into debate when data runs out. It revealed how deeply rooted assumptions about solid objects, comets, and asteroids really are. Most of all, it reminded scientists that the solar system is not sealed off. It is part of a larger galaxy where objects move freely, carrying unfamiliar properties and unexpected behaviors. The object is now far beyond the reach of our instruments, drifting through interstellar space, unchanged by the arguments it left behind. But the questions remain active, shaping research and fueling discussions. Was Oumuamua an icy fragment from a distant system, stripped bare by time and radiation? Was it something shaped by violent forces we rarely see? Was it a thin, reflective body pushed by light alone? Each possibility carries its own implications, and none can yet be ruled out completely. Long before Oumuamua, there were other objects on the books that raised similar alarms. Objects that should not exist in a stable form. Objects that looked solid when they should have been torn apart. Objects that appeared after violence so extreme that nothing recognizable should have survived. And once the shock of the first interstellar visitor began to settle, attention returned to something even more unsettling than a strange rock drifting through space. Attention returned to planets that had no right to still be planets at all. These were not planets orbiting calm stars like the Sun. These were objects circling pulsars, the crushed cores of exploded stars. In places where gravity is brutal, radiation is constant, and space itself feels hostile to structure. And among these remnants was one that stood out for a reason that sounded almost fictional when it was first described. A planet-sized object made largely of diamond. Planetary remnants made of diamond. The idea that a planet could be made mostly of diamond sounds like something pulled from science fiction, but the object that forced scientists to consider it was discovered in one of the harshest environments in the galaxy. This was not a young planetary system forming quietly inside a disk of dust and gas. This was a dead star system, a pulsar spinning hundreds of times per second, emitting beams of radiation so precise that they behave like cosmic clocks. And circling that pulsar was an object that defied everything scientists thought they understood about what survives when a star dies. The object is known as PSRJ 1719-1438b, and its existence alone raised uncomfortable questions. Pulsars are born from supernova explosions. When a massive star runs out of fuel, its core collapses violently, and the outer layers of the star are blown into space. The energy released in that moment is enough to briefly outshine entire galaxies. The shockwave tears through nearby space, and the radiation environment becomes lethal to anything nearby. Conventional thinking said that any planets close to such a star would be destroyed instantly. If they were not vaporized outright, they would be stripped apart by tidal forces or blasted by radiation until nothing remained. Yet here was a planetary remnant still orbiting the pulsar, close enough to complete an orbit in just over 2 hours. That alone suggested an object that was incredibly dense. To survive that close without being ripped apart, it had to possess immense internal strength. Measurements of its mass and size painted an even stranger picture. This was not a gas giant. It was not a rocky planet like Earth. Its density pointed to something far more compact, something dominated by heavy elements, something that could endure conditions that would shred normal planetary material. The explanation that slowly emerged was that this object was not a full planet anymore. It was the exposed core of a once much larger world. The outer layers had been stripped away over time, peeled off by the pulsar's radiation and gravity, leaving behind the densest part of the planet. That core, under pressures far beyond anything found naturally on Earth, had transformed its carbon content into crystalline form. In simpler terms, it had become diamond on a planetary scale. This was a physical conclusion based on density, composition models, and the behavior of carbon under extreme pressure. On Earth, diamond forms deep below the surface, where pressure forces carbon atoms into a rigid lattice. On this planetary remnant, the pressures were orders of magnitude higher. The result would not be gemstones scattered through rock, but a structure dominated by crystalline carbon throughout much of its volume. The problem was not whether diamond could form. The problem was that the planet should never have survived long enough for this transformation to matter. The supernova that created the pulsar should have erased the system. Yet the object was there, orbiting steadily, silent proof that planetary material can endure far more punishment than models had allowed. This discovery forced scientists to rethink how planets interact with dying stars. It suggested that destruction does not always happen all at once. Instead of instant annihilation, planets can be slowly dismantled, layer by layer, over millions or even billions of years. As the pulsar spins and emits radiation, it heats the planet, strips its atmosphere if it has one, and gradually removes lighter elements. What remains is the hardest, densest material, compacted into a form that can resist further loss. This process changes the way astronomers think about planetary survival. It introduces a new category of object, something between a planet and a stellar remnant. These objects are not born as diamonds. They are carved into them by catastrophe. They represent what is left after nearly everything else has been erased. The discovery of PSRJ 1719-1438b did not happen through direct imaging. It was detected through its effect on the pulsar's timing. Pulsars emit beams of radiation with extreme regularity. Any wobble in that timing can reveal the presence of an orbiting object. By studying tiny shifts in the pulsar's signals, astronomers were able to calculate the mass and orbit of the companion. From those numbers came the realization that the object had a density too high for anything resembling a normal planet. As more pulsar planets were studied, similar patterns began to appear. Not all of them were diamond-rich, but several showed signs of extreme stripping and compression. These systems made it clear that planets can exist in places once thought completely hostile to structure. They also raised deeper questions about how common these remnants might be across the galaxy. If one such object exists nearby, there could be thousands more hidden around other pulsars, invisible except through their gravitational pull. What made this unsettling was the implication that planetary death is not always final. A star can explode, and yet something resembling a planet can remain, reshaped into something harder, denser, and stranger than before. This idea stood in sharp contrast to the clean, simple endings often taught in stellar evolution models. It suggested a messier universe, where destruction leaves behind survivors that do not fit neatly into existing categories. That same theme had already appeared with Oumuamua, a solid object traveling between stars, shaped by forces no one had expected, refusing to behave like known materials. The diamond planet was different in origin, but similar in message. Space does not always grind things into dust. Sometimes it compresses them into something tougher than what came before. The existence of diamond-rich planetary remnants forced scientists to confront a question they had rarely asked before. What actually happens to planets when their stars die? Why these objects force a rethink of planetary death? The old assumption was simple. Massive stars explode, smaller stars expand and shed their outer layers, and planets are either swallowed, burned, or flung into space. The details varied, but the outcome was assumed to be total destruction or ejection. The discovery of planets still bound to pulsars broke that assumption. What makes these objects especially difficult to accept is that they exist in an environment where physics is pushed to extremes. Pulsars have gravity strong enough to stretch objects into elongated shapes. Their radiation fields can strip atoms from surfaces. Their magnetic fields accelerate particles to near-light speed. Yet these planetary remnants remain intact, orbiting steadily, as if immune to conditions that should dismantle them. The explanation lies in density and composition. Once a planet loses its outer layers, what remains is no longer fragile. The core is compact, heavy, and tightly bound by gravity. As pressure increases, carbon atoms rearrange into more stable forms. Diamond is not fragile in this context. It is one of the strongest known crystal structures, capable of withstanding enormous stress. Under pulsar conditions, that strength becomes essential. This survival mechanism introduces a new phase in planetary evolution. Planets are no longer seen as objects with a single life cycle ending in destruction. Instead, they can pass through stages, shedding layers and transforming internally, leaving behind remnants that persist long after their parent stars have died. This idea reshapes how astronomers search for planets around dead stars and changes how they interpret unusual mass measurements in pulsar systems. the implications extend beyond individual discoveries. If planetary remnants can survive supernovae, then the number of planets in the galaxy may be far higher than current estimates suggest. Many may exist in altered forms, stripped down to cores, orbiting stellar corpses. These objects would be nearly impossible to detect unless they reveal themselves through timing effects or gravitational interactions. They would not emit light. They would not reflect much radiation. They would simply exist, dense and silent. This realization also feeds back into how scientists think about planetary composition in general. Carbon-rich planets were already considered possible under certain conditions, but the diamond remnant takes this idea to its extreme. It represents a natural outcome of physics operating under relentless pressure. It is not an exotic exception created by unlikely chemistry. It is the logical result of carbon being subjected to forces that leave no other stable option. In that sense, diamond planets are not rare accidents. They are endpoints. They are what happens when a planet is pushed as far as it can go without being erased completely. They are the fossilized cores of worlds that once had surfaces, atmospheres, and perhaps even oceans, reduced to something unrecognizable but still intact. The connection back to Oumuamua becomes clearer here. Both objects challenge assumptions about solidity in space. Oumuamua showed that solid objects can survive interstellar travel and behave in unexpected ways. Diamond planetary remnants show that solid objects can survive stellar death and extreme radiation while retaining structure. Both force astronomers to admit that their models often underestimate the resilience of matter. As telescopes improve and surveys expand, scientists expect to find more objects that fit neither traditional planetary categories nor stellar ones. Each new discovery adds pressure to theories that prefer clean lines and simple endings. Space does not offer those comforts. It offers continuity through transformation. Objects change form, not always by being destroyed, but by being stripped, compressed, and reshaped into something harder to recognize. These planetary remnants orbit silently, long after the violence that created them has faded. They do not announce themselves with flares or bursts. They reveal their presence only through subtle effects on the stars they circle. And yet their existence carries weight. It tells astronomers that even in the most violent corners of the galaxy, solidity is not easily erased. Matter adapts, it hardens, it survives. And just like the interstellar visitor that arrived without warning and left without explanation, these diamond worlds remain as quiet challenges to everything scientists thought they knew about how objects begin, change, and end in the universe. Now, the problem is no longer stars behaving badly or objects refusing to follow simple rules. The problem becomes scale. Entire regions of space begin to move in ways that do not match what we can see. Galaxies drift, not randomly, not slowly, but with purpose, pulled in a shared direction by something that refuses to show itself clearly. After interstellar objects like Oumuamua and planets stripped down to diamond cores showed that solid matter can exist in impossible forms, the universe takes another step further. Now the question is not how objects survive, but how entire structures form at all. What comes next is not a single star or a strange planet. It is something vast enough to affect tens of thousands of galaxies at once, something so massive that it bends the motion of the local universe, and yet remains partly hidden behind our own galaxy. This is where astronomers ran into a force they could not ignore, even though they could barely see it. The great attractor and the pull we cannot escape. In the early 1970s, astronomers began noticing something unsettling while mapping the motion of galaxies near the Milky Way. Galaxies were not just expanding away from each other as expected from the general expansion of the universe. Many of them were drifting in the same direction, as if being pulled toward a common destination. This motion was not subtle. It was strong, organized, and consistent across enormous distances. The galaxies were accelerating toward a region of space that appeared, at first glance, to be almost empty. This made no sense. According to known models of gravity, large-scale motion like this requires a massive source. The more mass something has, the stronger its gravitational pull. If thousands of galaxies were moving toward one area, that area should be filled with visible matter, clusters of galaxies, glowing gas, bright structures that telescopes could easily pick up. But when astronomers looked in that direction, they saw almost nothing. The region lay behind the dense dust and stars of the Milky Way, a part of the sky known as the zone of avoidance, where visible light surveys struggled to see clearly. Even accounting for that obstruction, the numbers did not add up. This unseen pull became known as the Great Attractor. It was not a single object, but a region of space exerting an enormous gravitational influence. Calculations suggested that the mass involved was equivalent to tens of thousands of Milky Way galaxies. That amount of mass should dominate its surroundings. It should be obvious. It should be bright. Instead, it was hidden, partially blocked, and strangely quiet. The idea that such a massive structure could exist without revealing itself challenged the way astronomers thought about cosmic organization. Gravity does not hide easily. Large clusters of galaxies glow in X-rays because of the hot gas trapped between them. They bend light through gravitational lensing. They announce their presence in multiple ways. Yet the Great Attractor seemed to do all of its work in the dark, revealing itself only through the motion of other galaxies. As more data came in, astronomers refined their maps of galaxy velocities. They confirmed that our own local group of galaxies, including the Milky Way, is moving at hundreds of kilometers per second toward this same region. This motion is not caused by the expansion of the universe alone. It is a local deviation, a directional flow, a sign that something nearby is reshaping the cosmic landscape. Infrared and radio observations began to peel back the Milky Way's obscuring dust. Behind it, astronomers found large galaxy clusters, including the Norma cluster, one of the most massive known clusters in the nearby universe. This explained part of the pull, but not all of it. Even when these hidden clusters were added to the calculations, there was still missing mass. The gravitational influence remained stronger than expected. This raised uncomfortable questions. Was there an even larger structure beyond what could be seen? Was dark matter playing a more dominant role here than anywhere else? Or was the Great Attractor part of something even larger, a superstructure extending far beyond a single region? As observations continued, the Great Attractor stopped being treated as a single mysterious object and began to look like part of a vast concentration of matter known as the Laniakea supercluster. This structure includes our own galaxy and stretches across hundreds of millions of light-years. The Great Attractor sits near its gravitational center, acting as a kind of anchor point. Even with this broader context, the original problem remains. Structures of this scale should take an immense amount of time to form. They require matter to clump together across distances so large that early cosmic conditions should have smoothed them out. The universe, according to standard models, began nearly uniform. Small fluctuations grew slowly under gravity. Large structures emerged later, not early. The Great Attractor and the supercluster it belongs to appear too organized, too massive, and too influential given the time available. It is not that such structures are impossible in theory. It is that their specific size, density, and gravitational reach strain the timeline that physics provides. What makes the situation more unsettling is how incomplete our view still is. Even with modern instruments, parts of the Great Attractor remain unseen. It continues to influence galaxy motion without fully revealing its shape. It is a structure defined more by its effect than by its appearance. That alone makes it stand out in a universe where most things announce themselves loudly. And while astronomers were still struggling to fully understand how something so massive could remain so hidden, another discovery pushed the problem in the opposite direction. Instead of regions with too much gravitational pull, scientists began finding regions with almost none at all. Cosmic voids that are too empty to explain. If the Great Attractor represents too much structure, too much mass, and too much influence concentrated in one place. Cosmic voids represent the opposite extreme. These are enormous regions of space with almost nothing inside them, very few galaxies, very little gas, vast stretches of near emptiness that span hundreds of millions of light-years. The problem is not just that these voids exist, it is how big and how empty some of them are. The discovery of large cosmic voids became possible with wide surveys, like the Sloan Digital Sky Survey, which mapped the positions of millions of galaxies across a large portion of the sky. When these maps were turned into three-dimensional models, the universe began to resemble a complex web. Galaxies traced out long filaments and walls, intersecting at dense nodes, while huge empty bubbles appeared in between. This large-scale structure became known as the cosmic web. Small voids were expected. They form naturally as matter flows toward denser regions under gravity. Over time, these empty regions expand as galaxies move away. But some of the voids discovered were far larger than predicted. One of the most striking examples is the Bootes void. The Bootes void spans roughly 330 million light-years across. Inside it, there are only a handful of known galaxies. To put that in context, a region of that size should contain thousands of galaxies if matter were distributed evenly. Even accounting for normal clustering, the emptiness of the Bootes void is extreme. It is not just underdense, it is almost completely hollow. This presents a serious challenge. Large voids should collapse or fragment over time as surrounding matter pulls inward. Instead, these voids appear stable and long-lived. Their boundaries are sharp, their interiors are remarkably clean. They are not filled with faint dwarf galaxies or clouds of gas. They are genuinely empty on a cosmic scale. The existence of such massive voids forces a rethink of how matter moves in the universe. Gravity alone struggles to explain why matter would evacuate such enormous regions so completely. Dark energy, which drives cosmic expansion, may play a role by accelerating the growth of voids, but even then, the scale remains difficult to justify. What makes the situation more complicated is how these voids interact with surrounding structures. Galaxies on the edges of voids tend to move faster than expected, as if pushed outward by the expanding emptiness behind them. This effect amplifies the contrast between dense filaments and empty regions, sharpening the cosmic web beyond what simple models predict. Some voids also show temperature differences in the cosmic microwave background, the afterglow of the Big Bang. These temperature shifts suggest that light passing through large voids loses energy due to the changing gravitational environment. This means voids are not passive absences. They actively affect the behavior of radiation and matter passing through them. In a strange way, cosmic voids mirror the great attractor. One represents too much gravitational influence concentrated in one region. The other represents a near-total lack of influence stretched across unimaginable distances. Both push against the limits of structure formation theory. Both exist at scales where small errors add up to major contradictions. The universe was expected to be messy but balanced, with matter and emptiness distributed in predictable ways. Instead, it presents extremes. Regions where gravity dominates far beyond expectations sit next to regions where almost nothing exists at all. These structures did not form gently. They carved themselves into the universe early and held their shape for billions of years. And that is what makes them so unsettling. They are not rare flukes. They are fundamental parts of the cosmic layout. The great attractor and vast cosmic voids are not exceptions at the edges of the universe. They are central features of how matter arranged itself on the largest possible scales. Their existence forces astronomers to confront a universe that organizes itself more aggressively, more unevenly, and more mysteriously than models once allowed. Between overwhelming gravitational pulls and yawning empty expanses, the universe shows a pattern that is anything but smooth. It forms structures that seem too big, too influential, or too empty to exist comfortably within our rules. And it does so without explanation, leaving behind motions, gaps, and flows that can be measured precisely, even when their true causes remain just out of reach. Fast radio bursts signals that shouldn't exist at all. Long before fast radio bursts had a name, radio astronomers were already used to strange noise. Space is loud in ways most people never think about. Stars hiss, pulsars click like broken clocks, galaxies hum faintly in the background. Radio telescopes are built to listen through that mess and pull out patterns that repeat, signals that make sense, sources that can be tracked and explained. Fast radio bursts did not behave like any of those things. They arrived without warning, vanished almost instantly, and left behind numbers that made no sense for how short they were. A fast radio burst lasts only a few milliseconds. That alone makes it strange, but the real problem shows up when energy is added to the picture. In that tiny slice of time, a single burst can release as much energy as the sun produces in days or even weeks. Nothing in known physics should be able to dump that much power so quickly without destroying itself. No star should survive it. No structure should hold together. Yet the signals kept coming, scattered across the sky, each one appearing once and never again, at least at first. The first time one was found, it was not even supposed to be there. In 2007, astronomer Duncan Lorimer and his student were going through old data from the Parkes Radio Telescope in Australia. They were not hunting for new cosmic mysteries. They were checking archival recordings, the kind of work that usually ends with nothing more exciting than calibration notes. Buried in that data was a bright radio pulse that lasted just a few milliseconds. It was far stronger than background noise and had a very specific signature that showed it had traveled through vast amounts of space. That signature mattered. As radio waves move through space, they pass through clouds of electrons. Lower frequency waves slow down more than higher frequency ones. This causes a delay called dispersion. The more material a signal passes through, the more spread out it becomes. The burst Lorimer found showed extreme dispersion. That meant it had crossed an enormous distance, far beyond the Milky Way. This was not interference. This was not a satellite. This was not a glitch in the equipment. It was a real signal that had crossed billions of light years and arrived on Earth by pure chance. That single burst raised an uncomfortable question. If something could release that much energy in milliseconds and still exist long enough for the signal to reach us, then there were objects in the universe doing things no model had predicted. At the time, many astronomers were cautious. Some assumed it was a one-off event or a rare fluke. Others wondered if it could be human interference that slipped through filters. For several years, fast radio bursts remained an odd footnote, interesting but unproven. That changed when another one appeared, then another, different telescopes, different parts of the sky, same pattern. Each burst arrived fast, bright, and gone almost immediately. The dispersion measurements kept pointing to distances far outside our galaxy. Fast radio bursts were real, and they were happening often. Estimates now suggest thousands occur every day across the observable universe. Most of them never hit Earth, but enough do to prove they are common. The problem grew larger with every detection. The energy involved ruled out many familiar sources. Supernova explosions release huge amounts of power, but they last seconds to minutes and destroy the star in the process. Pulsars emit radio waves, but in regular repeating patterns tied to rotation. Fast radio bursts were chaotic, brief, and often one-time events. Any object producing them would need an extreme energy source, a way to release it almost instantly, and some method of surviving afterward. Early theories spread in all directions. Some involved merging neutron stars, others pointed to collapsing objects or exotic plasma effects near black holes. A few ideas drifted into speculation that never gained serious support. What mattered was that none of the standard explanations worked cleanly. Each idea fixed one problem and created another. A merger could release enough energy, but it would only happen once. That fit non-repeating bursts, but failed to explain later discoveries. Those later discoveries changed everything. In 2012, Astronomers detected a fast radio burst that repeated. It came from the same location again and again. That single fact broke half the existing theories overnight. Whatever produced that signal was not destroying itself. It was surviving and firing again. This object was capable of releasing massive energy bursts without tearing itself apart. Repeating fast radio bursts created a split. Some bursts repeated, others did not. Some came from distant galaxies with intense star formation. Others came from quieter regions. The population was not uniform. This was not one phenomenon with one cause. It was a category, and inside that category were multiple engines doing similar things in different ways. As detection methods improved, localization became possible. Instead of vague sky positions, astronomers could trace bursts back to specific galaxies. One repeating burst was linked to a small dwarf galaxy with high star-forming activity. That environment suggested young, violent stellar remnants. The idea of magnetars entered the conversation more seriously. Magnetars were already known to release sudden powerful energy through magnetic field shifts. Their flares were violent, unpredictable, and capable of extreme power output. At first, the magnetar idea was treated carefully. Magnetars were rare, and no direct link had been proven. That changed in 2020. A magnetar inside the Milky Way, known as SGR 1935 plus 2154, released a burst of radio waves that matched the energy and structure of fast radio bursts detected from other galaxies. This event was weaker than the extragalactic bursts, but followed the same pattern. For the first time, astronomers observed a fast radio burst source up close. That moment did not solve the mystery. It complicated it. Magnetars could clearly produce fast radio bursts, but they could not explain all of them. Some bursts came from environments where magnetars were unlikely. Some showed energy levels that pushed magnetar models to their limits. Others repeated in patterns that did not match known magnetar behavior. The universe was not offering a single answer. It was offering a collection of partial ones. The physics behind the bursts remained brutal. Compressing that much energy into milliseconds required conditions far beyond anything humans could replicate. The emission mechanism itself became a puzzle. Radio waves are low energy compared to gamma rays or X-rays, yet these radio bursts were astonishingly powerful. Something was converting stored energy into radio emission with extreme efficiency. That process alone challenged existing plasma physics. Another layer of confusion came from polarization. Many fast radio bursts showed twisted polarization patterns, meaning the radio waves were rotating as they traveled through strong magnetic fields. Some rotations were so extreme that the source had to be surrounded by dense, magnetized plasma. This pointed again toward young neutron stars or extreme environments near black holes. Still, no single model covered all observed features. Then there was the timing. Some repeating bursts fired randomly. Others showed active periods followed by silence. One source even displayed a rough cycle, active for weeks, quiet for months, then active again. That kind of behavior suggested orbital motion or precession, something rotating or wobbling on a regular schedule. Theories multiplied. Binary systems, magnetars orbiting massive stars, magnetars near black holes. Each idea worked in isolation and failed in combination. The more data arrived, the stranger the population looked. Non-repeating bursts tended to be more energetic. Repeating bursts were often weaker but persistent. Some bursts showed fine structure inside the milliseconds, tiny subpulses separated by microseconds. That implied emission regions only kilometers across, changing faster than most known stellar processes. Fast radio bursts also became tools. Their dispersion allowed astronomers to measure the matter between galaxies. Each burst acted like a flashlight passing through cosmic fog. Variations in the signal revealed information about intergalactic plasma that was otherwise invisible. Even without understanding their sources completely, fast radio bursts became probes of the large-scale universe. Despite that usefulness, the core mystery remained untouched. Objects were releasing impossible amounts of energy on impossible timescales. Some survived to do it again. Others vanished forever after a single flash. There was no warning and no reliable way to predict when the next one would appear. Telescopes had to be watching constantly, hoping to be looking in the right direction at the right moment. The catalogue grew into the hundreds, then the thousands. New arrays like CHIME transformed detection rates, catching bursts almost daily. Patterns emerged slowly, then broke again with new data. Each new instrument added clarity and confusion in equal measure. Fast radio bursts no longer sat on the edge of astronomy. They cut through it. They forced revisions in neutron star physics, plasma behavior, magnetic field dynamics, and energy transport. They showed that the universe could compress violence into moments so brief that human senses could never experience them directly. Even the Milky Way example did not calm the debate. That galactic burst proved magnetars could do it, but it did not prove magnetars were always responsible. It simply added another confirmed source to a list that was already growing. The question shifted from, what causes fast radio bursts, to how many different things can. That uncertainty kept the field alive. No single explanation dominated. No final model closed the case. Fast radio bursts remained signals without clear origins, not because of a lack of effort, but because nature refused to limit itself to one clean mechanism. They arrived, they vanished, and they left behind data that forced astronomers to accept that the universe was capable of concentrating power in ways no theory had anticipated. And while some sources could now be named, many others stayed silent forever after a single outburst, leaving no trace beyond a few milliseconds of radio light stretched across billions of years of travel. Objects that defy classification. The universe has a way of surprising us. Just when astronomers think they've categorized everything, a completely new type of object appears, refusing to fit any existing models. These are the cosmic rebels, the things that refuse to be defined, that push the boundaries of what we think is possible. Among these, luminous red novae and unclassified transient events are some of the most perplexing discoveries in modern astronomy. Their existence is more than just an oddity. It forces scientists to rethink the very framework of how stars evolve, die, and interact. Luminous red novae are events so peculiar that they initially confounded astronomers. Unlike typical novae or supernovae, which either explode with immense brightness or gradually fade after a standard pattern, luminous red novae behave unpredictably. Their light curves are unusual, often showing sudden rises and slow fades that do not align with known nuclear reactions in stellar cores. Their colors are deep red, a signature that indicates lower temperatures than expected for such energetic outbursts. The first of these objects was observed decades ago, but only with modern telescopes and advanced imaging technology have we begun to appreciate just how strange they are. These are not explosions in the conventional sense. They are often associated with stellar mergers, where two stars collide and merge into a single, larger star. But even this explanation only partially accounts for the behavior we see. Some luminous red novae show properties that do not match merger models, leaving astrophysicists scratching their heads and running new simulations to understand how energy, mass, and light interact in these extreme environments. Unclassified transient events take this mystery a step further. They appear suddenly in the sky, shining intensely for a brief moment before vanishing, leaving behind little to no trace. These events do not fit any known category of stellar explosion. They are not supernovae, novae, gamma-ray bursts, or magnetar flares. Some repeat irregularly, while others appear once and never return. Their durations vary, their energy outputs are unpredictable, and they often originate from regions of space where no significant stellar population is present. The sheer randomness of these events makes them difficult to study. They require continuous monitoring and rapid response from observatories across the world, using multi-wavelength imaging to capture as much data as possible before the phenomenon fades. Each observation challenges current theories of stellar life cycles, forcing astronomers to consider new mechanisms of energy release and interaction in environments that are still largely unknown. The reason these objects are so important is that they defy existing categories. For centuries, astronomers have relied on classification systems to make sense of the universe. Every star, nova, supernova, or black hole has a defined type, with predictable behavior based on mass, composition, and age. Luminous red novae and unclassified transients do not adhere to these rules. They demonstrate that our understanding of stellar physics, explosive mechanisms, and energy propagation is incomplete. The discovery of a single object that refuses classification can ripple across multiple fields of astrophysics, altering models of galaxy formation, stellar evolution, and even cosmology itself. The way astronomers detect these objects is also worth noting. Unlike ordinary stars, which can be observed consistently over long periods, transient events require constant surveillance. Surveys like the Sloan Digital Sky Survey and other large sky mapping projects play a crucial role. They scan vast portions of the sky nightly, capturing sudden changes in luminosity. Once an unclassified transient is detected, telescopes at different wavelengths, from radio to X-ray, are trained on the source to gather additional data. This multi-wavelength approach is essential, as it reveals characteristics that a single spectrum cannot. Some events emit radio waves before visible light appears. Others produce X-ray or ultraviolet signatures without corresponding optical counterparts. Understanding these patterns helps scientists build hypotheses about what mechanisms could produce such sudden and unusual phenomena. In addition to observational techniques, simulations and theoretical modeling have become central to studying these bizarre objects. Computer models allow astronomers to recreate the extreme conditions that may produce luminous red novae or unclassified transient events. They can manipulate mass, density, magnetic fields, and temperature to see how stars might behave under different circumstances. These simulations have revealed that minor variations in initial conditions can lead to radically different outcomes, offering one explanation for why some transient events do not repeat or why their light curves are so irregular. Even with these models, however, many of the observed behaviors remain unexplained, emphasizing how little we truly understand about the physics governing these extreme objects. The connection between these unclassified transients and other phenomena. Another fascinating aspect is the potential connection between these unclassified transients and other phenomena, such as fast radio bursts or magnetar flares. While the connection is not fully established, some transient events appear to occur in regions where magnetars are also present, raising questions about whether similar extreme magnetic fields could play a role. Additionally, some luminous red novae occur in binary star systems where complex gravitational interactions may trigger unusual outbursts. The overlap of observational evidence across different types of cosmic anomalies suggests that the universe may have common underlying mechanisms that manifest in unpredictable ways, defying simple classification. Observing these objects has also revealed surprises about their environments. Many luminous red novae are found in older star clusters, where conventional stellar evolution predicts that most stars should be stable or nearing the end of their life cycles. The appearance of a sudden energetic event in such a population is unexpected and challenges models of cluster dynamics and star formation. Unclassified transients, meanwhile, have been spotted in remote galactic halos and intergalactic space, far from the dense stellar populations that would typically fuel explosive events. These discoveries indicate that extreme stellar behavior can occur under conditions previously thought impossible, further expanding the boundaries of what astronomers consider viable in stellar physics. The pace of discovery in this field has accelerated dramatically over the past 2 decades. Advances in telescope sensitivity, high-speed imaging, and real-time data processing allow astronomers to capture transient events that would have gone unnoticed in previous generations. Projects like the Large Synoptic Survey Telescope, now operational as the Vera Rubin Observatory, are expected to increase the detection rate of these anomalies by orders of magnitude. Every new object detected adds another layer of complexity to the models and forces scientists to refine their understanding of the underlying physics. Each observation is a reminder that the universe is far stranger than our current classifications can accommodate. Scientific debate over the nature of these objects is intense. Luminous red novae, for instance, have been interpreted as evidence for stellar mergers, but the diversity in observed behavior raises questions about whether a single mechanism can explain all instances. Some transients exhibit energy outputs that seem too low or too high for the proposed models. Others have spectral characteristics that suggest processes involving magnetic fields, nuclear reactions, or gravitational dynamics that are not yet fully understood. The need for peer-reviewed research, simulation verification, and corroborating observational evidence is crucial, yet the rapid appearance and disappearance of these events make the work painstakingly slow. In addition to their physical properties, these unclassifiable objects impact the way astronomers plan and execute observations. Traditional methods rely on predictable cycles, whether monitoring a star cluster or tracking a known variable star. The unpredictable nature of luminous red novae and transient events requires flexible scheduling and rapid coordination across multiple observatories. Ground-based telescopes, space-based instruments, and even amateur astronomers play roles in tracking these phenomena. Alerts must be issued in real time to capture fleeting signals, and data must be shared quickly to maximize scientific return. The collaborative nature of these discoveries highlights how modern astronomy has evolved into a global effort to understand objects that defy conventional classification. The theoretical implications extend beyond stellar physics. The unexpected behavior of luminous red novae and unclassified transients challenges assumptions about energy generation, angular momentum conservation, and mass distribution in stars. If stars can merge or undergo explosive outbursts under conditions previously thought stable, it raises questions about how galaxies evolve, how star clusters age, and even how heavy elements are distributed throughout the cosmos. These objects act as natural laboratories for phenomena that cannot be recreated on Earth, allowing scientists to probe extreme physics in a way that bridges observation and theory. Technology has also played a transformative role. Instruments capable of high-speed photometry, wide-field imaging, and multispectral analysis allow astronomers to capture the fine details of transient events. Spectroscopic analysis reveals the chemical composition of ejected material, while imaging captures the motion and expansion of stellar debris. These detailed observations are critical for testing models of energy release, radiation transfer, and stellar dynamics. Each piece of data provides a puzzle piece that, when combined with others, gradually reveals the underlying mechanisms behind these enigmatic objects. The unpredictable nature of these phenomena continues to challenge even the most seasoned astronomers. Luminous red novae may brighten in unexpected ways, producing secondary peaks that defy current models. Some unclassified transient events appear near regions of active star formation, while others emerge from seemingly empty space, suggesting a wide range of potential progenitors. This diversity complicates efforts to generalize findings or create a unified classification system. The very definition of what constitutes a nova or a transient is being questioned as more unusual cases are discovered, highlighting the limits of existing astronomical taxonomy. Another layer of complexity comes from the interplay between observation and simulation. While computational models can replicate many aspects of luminous red novae, discrepancies remain in predicting light curves, energy output, and spectral signatures. Simulations often require assumptions about initial conditions, mass ratios, and magnetic fields that are difficult to verify observationally. Unclassified transients are even harder to model due to the lack of repeated events and limited data. Despite these challenges, modeling remains essential, providing a framework to interpret observations and to hypothesize the physical processes at work. The study of these objects also influences the design of future astronomical instruments. Telescopes with faster readout times, wider fields of view, and greater sensitivity to specific wavelengths are being developed to capture more transient events. Space-based observatories complement ground-based systems, providing coverage in spectral ranges inaccessible from Earth. The combination of advanced technology and coordinated observation networks ensures that as more of these enigmatic objects appear, astronomers will be prepared to capture them in unprecedented detail. The discoveries of luminous red novae and unclassified transient events have far-reaching implications for understanding the life cycles of stars. They demonstrate that stellar evolution is not always a predictable linear process. Stars can behave in unexpected ways, releasing energy through mechanisms that challenge our comprehension of nuclear physics, gravitation, and magnetism. Each new event contributes to a growing body of evidence that the universe contains phenomena beyond existing theoretical frameworks, forcing a continuous reassessment of what is possible in astrophysics. Even with all these insights, the mystery deepens. The objects continue to appear in unexpected locations at unforeseen times and with varying properties that defy explanation. The unpredictability forces astronomers to remain vigilant, constantly scanning the sky and updating their models. Each observation, spectrum, unusual light curve provides clues to the underlying physics, yet the complete picture remains elusive. The universe in these moments is a vast laboratory where rules are tested, broken, and rewritten in ways that challenge the limits of human understanding. What these objects are doing to modern science. The universe does not follow our rules. Every time astronomers think they have it figured out, the cosmos throws another curveball. Black holes that form too early, magnetars with impossible magnetic fields, fast radio bursts that flash and vanish in milliseconds, luminous red novae that refuse classification. All of these discoveries have something in common. They challenge the very foundations of physics. They are not anomalies to be dismissed, but data points screaming that our models of reality are incomplete. When scientists observe a magnetar, they see a star whose magnetic field could distort atoms themselves. Fast radio bursts arrive from galaxies billions of light years away, unleashing energy equivalent to the sun's lifetime output in just milliseconds. Rogue black holes drift invisibly across the galaxy, undetectable until they bend light from distant stars. Oumuamua came hurtling through the solar system, a strange interstellar visitor accelerating without an obvious force. Planetary remnants of diamond orbit pulsars, entirely surviving the death of their stars. Cosmic voids stretch across hundreds of millions of light years, emptier and larger than the standard cosmological models allow. Each of these discoveries is a puzzle piece, but one that does not fit neatly into any existing framework. The first impact these objects have on science is that they force revisions to physical models. A model is essentially a set of rules and equations that describes how nature works. These models are built from centuries of observation, experimentation, and theory. For example, the standard model of stellar evolution predicts how stars live, age, and die based on their mass and composition. It worked well for most stars in the Milky Way. But then came the blue stragglers, stars that appear younger than their peers, and the universe had to confront a fact that defied expectations. Suddenly, stellar lifespans could no longer be taken as fixed. Collisions, mergers, and interactions needed to be incorporated into the model. Magnetars demanded even more drastic adjustments. The intense magnetic fields they generate could not be explained by traditional neutron star models. Suddenly, quantum electrodynamics under extreme magnetic fields became a necessary part of astrophysical theory. The energy output of a single flare could influence entire planetary atmospheres across thousands of light years. Models that previously ignored such scales had to be updated. Beyond revising old models, these objects have prompted new simulations at a level of detail that was unimaginable a few decades ago. For a long time, scientists could only theorize about what happens inside a supernova or a neutron star. They had equations describing gravity, thermodynamics, and nuclear physics, but they could not observe these conditions directly. Now, with the discovery of objects like SGR 1806-20 and fast radio bursts from galactic magnetars, simulations must replicate extreme conditions with high precision. Researchers build virtual stars, feeding in magnetic fields trillions of times stronger than Earth's, and watch how the star's crust might fracture. They simulate black holes forming in the first billion years of the universe, attempting to explain how supermassive objects could exist when the cosmos was barely a few 100 million years old. These simulations are not trivial. They require enormous computational power, running on supercomputers for weeks, sometimes months, to account for even a fraction of the variables involved. But without them, the physics of these extreme objects would remain a black box, a set of observations with no theoretical underpinning. These discoveries have also expanded observation programs in unprecedented ways. Traditional astronomy relied on targeted observations. Telescopes pointed at a specific star or galaxy, observations scheduled over months or years. But transient objects, fast radio bursts, unclassified novae, rogue black holes, do not announce their appearance in advance. They demand constant vigilance. Sky surveys are now automated, capturing vast sections of the sky every night. Instruments like the Vera Rubin Observatory and the Pan-STARRS survey scan for sudden changes in brightness or position. Space-based observatories, such as the James Webb Space Telescope, supplement these ground-based efforts with infrared and X-ray imaging. The combination of continuous wide-field monitoring and rapid follow-up allows scientists to catch events that would have been impossible to detect just a decade ago. These new programs do more than collect data. They redefine how astronomy is done, shifting from a static to a dynamic real-time exploration of the cosmos. The ripple effect on physics. The influence of these objects extends far beyond astronomy into fundamental physics. Take fast radio bursts, for example. The millisecond flashes challenge our understanding of energy transfer, magnetic reconnection, and relativistic particle acceleration. Observations suggest that some FRBs are produced by magnetars, objects that themselves challenge atomic physics with their extreme fields. Modeling the generation of FRBs requires integrating quantum mechanics, general relativity, and plasma physics, fields that were traditionally studied independently. This intersection of disciplines is driving a new kind of astrophysics, one that embraces complexity and rejects the notion that the universe can be simplified into neat, isolated systems. Rogue black holes similarly push the boundaries. These objects drift invisibly, detectable only when their gravitational field bends the light of background stars. Detecting and tracking them requires understanding gravitational microlensing at a level that was largely theoretical until recent observations confirmed the first isolated stellar mass black hole. The implications are profound. These objects carry information about the formation and evolution of galaxies, the distribution of dark matter, and the frequency of stellar deaths. Observing them refines models of galactic dynamics, but it also challenges the limits of our instrumentation, requiring new methods of detection and analysis. Even objects like Oumuamua influence science in subtle but profound ways. Its shape and acceleration defied all previous models of interstellar bodies. Some suggested hydrogen ice, others nitrogen ice, and some even proposed exotic outgassing mechanisms that had not been seen before. The debate surrounding this one object forced astronomers to reconsider the mechanics of small bodies traveling between stars. It also led to policy changes in how interstellar objects are tracked, requiring rapid identification and observation strategies that were non-existent prior to 2017. Oumuamua became a case study in adaptive science, demonstrating how a single unexpected object can restructure protocols across an entire discipline. Planetary remnants made of diamond illustrate another layer of impact on modern science. The discovery of planets orbiting pulsars, composed largely of crystallized carbon, revealed that planets could survive stellar death in ways previously thought impossible. These objects forced revisions in our understanding of planetary formation and survivability. The density, composition, and orbital mechanics of these remnants inform models of how stars explode, how planetary systems endure, and even how elements are distributed throughout the galaxy. They provide rare empirical data that test simulations and theories at extremes that cannot be replicated on Earth. The great attractor and cosmic voids further stretch the limits of cosmology. These massive structures, or absences of structures, confound models of how matter is distributed on the largest scales. The great attractor, a gravitational anomaly hidden behind the Milky Way, exerts influence over thousands of galaxies, yet remains partially unseen. Cosmic voids, enormous regions almost entirely devoid of matter, are larger and emptier than theory predicts. Observations of these structures challenge assumptions about the uniformity of the universe and the processes that shaped its large-scale structure. Scientists must now account for anomalies that cannot be ignored, refining simulations of cosmic evolution, and even reconsidering the role of dark matter and dark energy in shaping the cosmos. The discovery of these objects has also prompted cross-disciplinary collaboration in ways previously rare. Understanding luminous red novae or unclassified transients requires input from nuclear physicists, stellar dynamicists, and computational modelers. Understanding fast radio bursts requires expertise in plasma physics, magnetohydrodynamics, and high-energy astrophysics. Rogue black holes demand knowledge of gravitational lensing, astrometry, and galactic evolution. The challenges posed by these objects break down traditional silos in scientific research, encouraging collaboration across fields that historically worked independently. This collaborative approach accelerates discovery and ensures that new data is interpreted in a comprehensive, multidimensional context. Technology has followed these scientific demands. High-speed imaging, multispectral observatories, and automated detection algorithms are now standard in modern astronomy. Instruments must operate continuously, capable of capturing transient events that appear and vanish in seconds. Machine learning and AI are increasingly employed to sift through vast data sets, identifying anomalies that might otherwise go unnoticed. The synergy between observational capabilities and computational modeling allows scientists to not only detect, but also understand and predict the behavior of objects that were once considered anomalies. One of the most striking effects of these discoveries is their influence on educational and research priorities. Universities and research institutions now offer programs specifically designed to study transient phenomena, extreme astrophysics, and computational modeling at cosmic scales. Students are trained to think in terms of dynamic, unpredictable systems rather than static, predictable stars. Research grants are increasingly allocated to projects that investigate objects that defy classification or that challenge existing models. In this way, the universe is shaping the very structure of scientific inquiry, incentivizing curiosity-driven research into phenomena that might otherwise be dismissed as outliers. The sheer diversity of these extreme objects highlights the limits of traditional observational methods. Where telescopes once tracked predictable patterns over years, they must now be able to capture sudden, fleeting events. This has led to the establishment of global networks of observatories working in concert, coordinating observations across multiple wavelengths and time zones. Alerts must be disseminated rapidly, sometimes within seconds, to ensure that no data is lost. The logistical challenge is enormous, but it is driven entirely by the need to study objects that do not conform to expected behavior. At the heart of this transformation is the recognition that anomalies drive progress. Each discovery, whether a magnetar flare, a fast radio burst, a rogue black hole, or a luminous red nova, provides an opportunity to test the limits of physics, to refine simulations, and to enhance observational programs. The objects themselves are not just curiosities, they are catalysts, pushing the scientific community to expand its toolkit, rethink assumptions, and embrace the unexpected. The impact is also cultural within the scientific community. Papers on these objects often spark debate, disagreement, and collaboration. Conferences are filled with discussions about mechanisms that might produce unusual bursts, flares, or gravitational anomalies. These debates, often intense and sometimes contentious, are crucial to the process of refining hypotheses and models. They underscore the dynamic nature of modern astrophysics, where the universe determines the questions to be asked. The role of new telescopes in exploring the impossible. The universe is full of things that feel impossible. Magnetars spinning in space with magnetic fields so strong they could bend atoms, fast radio bursts that appear out of nowhere and vanish in milliseconds, rogue black holes drifting through the Milky Way unseen, and strange interstellar visitors like Oumuamua accelerating without any clear explanation, stars that refuse to age, planets made of diamond, and cosmic voids that stretch farther than models say they should exist. Each discovery makes it clear that space is far stranger than the stories we tell ourselves in textbooks. Nothing is as simple as it seems. The universe does not work in neat boxes, and the objects in it do not follow predictable patterns. These discoveries reshaped how astronomy is done. Telescopes now had to keep pace with the universe's unpredictability. No longer could scientists point a telescope at a single star and wait for months. They needed instruments that could scan massive sections of the sky, detect sudden changes, and capture fleeting events. Objects like fast radio bursts appear and disappear in milliseconds. Rogue black holes hide entirely until a gravitational lensing event occurs. Luminous red novae rise quickly and fade, leaving only faint traces behind. Capturing these events required new tools, faster reactions, and global collaboration. The James Webb Space Telescope changed everything. For the first time, astronomers could see into regions of space hidden behind clouds of dust, capturing infrared light that reveals objects invisible to optical telescopes. James Webb's infrared imaging detects subtle shifts and changes, mapping objects that would otherwise remain undetected. Planetary remnants around pulsars, some composed almost entirely of diamond, are detectable by the heat they emit in infrared wavelengths. These remnants orbit pulsars at incredible speeds, surviving the destruction of their parent stars, their crystallized cores providing evidence of conditions so extreme they cannot be replicated on Earth. The James Webb Space Telescope, launched into space to orbit beyond Earth's shadow, is the first of these revolutionary instruments. Unlike previous space telescopes, Webb is built to see the universe in infrared, allowing it to peer through thick clouds of cosmic dust and gas. Many of the universe's most unusual and extreme objects are hidden behind such curtains. Rogue black holes, for instance, emit no light of their own. They cannot be seen in the traditional sense, but their presence can warp the light from background stars. Webb's infrared imaging allows astronomers to detect subtle distortions and faint heat signatures that reveal these invisible wanderers. Each detection becomes a piece of the puzzle, showing where mass is concentrated and how these dark objects move through space. Webb's power is not limited to black holes. Fast radio bursts, though primarily observed in radio wavelengths, can have optical and infrared counterparts, especially when they occur in star-forming regions or interact with surrounding gas. Webb's infrared detectors capture faint emissions associated with these bursts, revealing the environment from which they originate. Magnetars, spinning neutron stars with impossible magnetic fields, can heat surrounding dust and gas, creating infrared signals that Webb can detect. This allows astronomers to see the aftermath of magnetar flares and study how their enormous energy affects nearby matter. The telescope's infrared vision is especially crucial for exploring the early universe. Supermassive black holes, far too large to have formed so soon after the Big Bang, reside in galaxies billions of light years away. The light from these galaxies has been stretched, shifted, and reddened over billions of years. Webb can detect these ancient signals, revealing the structure of the first galaxies and the conditions that allowed massive black holes to grow so rapidly. Each observation challenges our understanding of cosmic evolution and pushes scientists to ask new questions about how structures formed in the earliest epochs of the universe. Webb's instruments are capable of capturing extraordinary detail. Spectroscopy allows scientists to break down the light from distant objects, revealing their chemical composition, temperature, density, and motion. Infrared imaging can reveal hidden stars in dense clusters, uncover planets around pulsars, and detect remnants of stellar explosions. The telescope's stability and sensitivity make it possible to observe extremely faint objects that were previously beyond reach. Every photon captured is a clue, and the more Webb sees, the more it reshapes our understanding of what is possible in the universe. While James Webb excels at looking far and through dust, the Vera Rubin Observatory tackles a different challenge, monitoring the night sky in unprecedented detail. Unlike space telescopes, Rubin is ground-based, but it is designed to capture massive swaths of the sky with its wide-field camera. Every few nights, it images the entire observable sky visible from its location, producing terabytes of data that record changes in brightness, position, and color of millions of stars and galaxies. This continuous monitoring is essential for detecting transient events, phenomena that appear suddenly and vanish quickly. Fast radio bursts may be invisible to optical telescopes, but associated flares or light echoes from surrounding material can be detected by Rubin. Luminous red novae, which appear as sudden brightening events in distant galaxies, are captured in real time, allowing scientists to study their rise, peak, and fade in detail. The observatory's wide field is its greatest strength. Many rare events happen in unpredictable locations across the sky. Traditional telescopes could never hope to find them without prior knowledge. Rubin captures everything, creating an archive of changes across the universe that can be mined for patterns and anomalies. Blue stragglers, stars that refuse to age, can be studied across multiple globular clusters, providing statistical evidence for theories like stellar mergers or mass transfer in binaries. Cosmic voids and large-scale gravitational anomalies can be mapped by tracking the motion of galaxies over vast distances. Each observation contributes to a broader understanding of the universe's structure and behavior. Data from Rubin is fed into automated systems that flag unusual changes. Astronomers no longer rely solely on luck or human observation. Alerts can be sent to other telescopes worldwide, enabling multi-wavelength follow-up. A sudden brightening could trigger immediate observations in infrared, X-ray, or radio bands, revealing additional information about the event. The observatory turns the unpredictable sky into a continuous flow of discoveries, capturing events that last hours, days, or mere seconds. This capability is reshaping how transient astrophysics is approached, making it possible to study extreme phenomena systematically, rather than as isolated curiosities. Complementing Webb and Rubin are next-generation radio arrays, designed to capture the universe in wavelengths invisible to optical and infrared telescopes. Fast radio bursts are their primary focus, mysterious flashes of energy lasting milliseconds, some repeating, some singular. These arrays, including instruments like CHIME, ASCAP, and the upcoming Square Kilometre Array, can detect hundreds of bursts in a single year, tracing them back to their source with remarkable precision. Pinpointing their locations allows astronomers to study their environments, identifying whether they arise from magnetars, neutron star collisions, or unknown mechanisms. Radio arrays excel at capturing details of the bursts themselves. Polarization measurements reveal magnetic fields, frequency drift reveals plasma conditions, and timing analysis uncovers patterns in repeating sources. When combined with optical and infrared observations from Webb or Rubin, these measurements allow scientists to reconstruct entire astrophysical events in multiple dimensions. The arrays also detect longer-term phenomena, such as emissions from pulsars, supernova remnants, or gravitational interactions in binary systems. They provide a window into processes that occur at scales and energies impossible to reproduce on Earth. The coordination between these telescopes creates a new model of observational astronomy. Webb sees the faint, distant, and dust-obscured universe. Rubin monitors millions of stars and galaxies for sudden changes. Radio arrays capture energy that no optical instrument can detect. Together, they allow astronomers to trace complex phenomena from multiple perspectives. A fast radio burst detected by a radio array can be followed by Webb to study the surrounding galaxy. Rubin can confirm whether any visible light or flare accompanied the burst. Rogue black holes can be identified by Rubin and confirmed through Webb's infrared imaging. Luminous red novae can be tracked across bands, revealing their chemical composition, expansion, and energy output. This multi-telescope approach provides the only way to understand extreme objects that defy simple classification. These instruments also push the limits of what we can see in real time. Webb can capture light that has traveled billions of years. Rubin can detect events that last only days. Radio arrays can detect phenomena lasting milliseconds. Together, they transform how astronomy is done, making it possible to study a dynamic, constantly changing universe. The telescopes do not just observe, they allow science to interact with events that are fleeting, rare, and extreme. The universe no longer waits for our instruments. Now, our instruments chase the universe's most bizarre objects, capturing them as they happen. Even objects that seem small or insignificant become significant with these tools. A single rogue black hole bending starlight or a faint planetary remnant emitting infrared radiation becomes a window into extreme physics. Fast radio bursts illuminate the processes in magnetar environments, revealing physics under conditions impossible to replicate. Luminous red novae teach about stellar collisions and mass ejections. Interstellar visitors like Oumuamua offer insight into material from other star systems. Each discovery depends on the capability, sensitivity, and coordination of these telescopes, which together turn fleeting events into analyzable data. Webb, Rubin, and radio arrays also redefine observational strategy. Multi-wavelength campaigns become standard. Alerts from one telescope trigger follow-ups from others. Real-time data sharing allows global teams to respond immediately. The sky is no longer a static canvas, but a dynamic environment full of events waiting to be captured. The telescopes themselves shape the science, dictating what can be seen and when, and enabling studies of objects that were previously invisible or transient. The precision of these instruments also opens doors to new kinds of discoveries. Webb can resolve structures in early galaxies, revealing how supermassive black holes formed. Rubin can map large-scale structures, including cosmic voids and gravitational anomalies like the Great Attractor. Radio arrays can localize fast radio bursts and probe magnetic fields in distant galaxies. Together, these observations provide a multi-dimensional understanding of objects that break rules, exist in extreme conditions, and challenge everything we thought we knew about the cosmos. These new telescopes do more than capture what was previously hidden. They transform how science itself is done. Observing fast radio bursts reveals their complexity. Some repeat with patterns, some vanish completely, some appear alongside magnetar flares, others in completely unrelated regions. Each detection adds pieces to a puzzle that scientists are only beginning to understand. Magnetar flares are observed simultaneously in X-ray, optical, and radio bands, showing how the starquakes release energy through different channels. Luminous red novae's light curves are captured in detail, revealing chemical signatures and explosion mechanics that simulations previously missed. Rogue black holes reveal their presence in minute distortions of starlight across multiple observatories, which must be precisely measured to distinguish them from ordinary gravitational lensing. The telescopes also create enormous datasets. Every night, Vera Rubin captures millions of stars. James Webb observes faint galaxies, and radio arrays track thousands of fast radio bursts. These datasets allow scientists to study populations of objects rather than single events. Blue stragglers in globular clusters, for example, can be analyzed statistically, revealing patterns in mass transfer or merger frequency. Observing dozens of cosmic voids provides information about their size, distribution, and emptiness, challenging models of large-scale structure formation. Every dataset is a map of chaos, revealing patterns only visible when millions of events are considered together. Simulations now integrate data from these telescopes to model the extreme conditions seen in magnetars, fast radio bursts, and luminous red novae. Trillions of magnetic field lines are modeled, particles accelerated to near-light speed, and supernova remnants tracked through interstellar space. Rogue black holes are inserted into galactic models, allowing scientists to see how they influence star motion and gravitational structure. Each simulation is a test of physics at limits far beyond anything achievable on Earth. It combines observations, theory, and computation into a single tool that can predict behavior, which is then verified by new observations. Even small objects like interstellar visitors are studied with extraordinary detail. Oumuamua's strange acceleration and shape sparked debates about hydrogen ice, nitrogen ice, and exotic outgassing mechanisms. Each hypothesis had to be tested with models informed by observations across multiple wavelengths. The discovery prompted policy changes for interstellar tracking, ensuring that future visitors are caught quickly and studied comprehensively before they vanish. James Webb and Vera Rubin now provide the tools to detect such objects earlier, and radio arrays can capture any emissions, revealing clues about their composition, origin, and structure. Planetary remnants made of diamond-orbiting pulsars are another window into extreme physics. These planets survived their star's death, existing as crystalline cores of carbon, orbiting neutron stars with incredible density and speed. Observing their thermal signatures and orbits requires infrared imaging, high-resolution timing, and coordination between instruments. These remnants provide insight into planetary formation, survival under extreme conditions, and even the distribution of heavy elements in the galaxy. Their existence proves that planets can endure what should be total annihilation and opens questions about the resilience of planetary systems throughout the cosmos. Cosmic voids and massive gravitational anomalies like the Great Attractor also require new observation strategies. Infrared and radio telescopes penetrate galactic dust to reveal structures hidden behind the Milky Way. Surveys like those from Vera Rubin capture galaxy motions, mapping how clusters are drawn toward massive unseen objects. Radio arrays can detect faint emissions, indicating the presence of massive gravitational sources. Together, these tools allow scientists to map the invisible, revealing the skeleton of the universe, its empty spaces, and its hidden masses, all of which were invisible to older instruments. The coordination of these telescopes is unprecedented. Real-time alerts allow instruments around the world to respond to transient events immediately. Observatories share data across continents, capturing different aspects of the same phenomenon. When a fast radio burst is detected, space telescopes, ground-based optical observatories, and radio arrays all monitor it simultaneously. Rogue black holes bending light are tracked over weeks by multiple instruments to confirm their presence. Luminous red novae are studied continuously from rise to fade across wavelengths, revealing details that were invisible before. Every event becomes a collaborative project, combining instruments, data, and expertise to understand phenomena that were previously inaccessible. Even the smallest details matter. Minute changes in brightness or color can indicate exotic materials, unusual nuclear reactions, or unexpected energy transfer. Fast radio bursts show subtle variations in frequency that hint at magnetic environments, relativistic motion, and interstellar medium effects. Luminous red novae provide spectra that reveal molecular formation and stellar collisions. Planetary remnants show thermal emissions, revealing their composition and orbit. Each observation, no matter how small, contributes to a larger understanding of extreme objects and the physics that governs them. New telescopes are not just tools, they define what can be seen, measured, and understood. Without James Webb, rogue black holes might remain invisible, diamond planets undiscovered, and early supermassive black holes unreachable. Without Vera Rubin, transient events could be missed entirely, statistical patterns unobservable, and rare phenomena overlooked. Without next-generation radio arrays, fast radio bursts would remain mysterious flashes, and the magnetic and energetic processes behind them would remain hidden. These instruments are a bridge between the impossible and the observable, revealing a universe far stranger and more dynamic than anyone imagined. Limitations of observation. The universe has a habit of surprising us. Every time astronomers think they understand how stars live and die, how galaxies form, or how matter behaves under extreme conditions, the cosmos pushes back. Strange objects appear in the sky. Events unfold that defy equations, and suddenly what seemed impossible is no longer theoretical. It is reality. Magnetars with magnetic fields trillions of times stronger than Earth, fast radio bursts flashing across galaxies in milliseconds, rogue black holes wandering silently through the Milky Way, interstellar visitors like Oumuamua. Each of these discoveries challenges the very framework scientists rely on to make sense of space. What makes these events feel impossible is often not the universe itself, but the limits of our understanding and our instruments. Science depends on observation, prediction, and theory. But observation is never complete. Even with the most powerful telescopes, we see only slices of the sky, snapshots in time, and a tiny fraction of the electromagnetic spectrum. Some phenomena are fleeting, others faint, and some are invisible to all but the most specialized instruments. The universe does not wait for scientists to be ready. Rogue black holes drift unseen until their gravity warps starlight. Fast radio bursts vanish before telescopes can react. Luminous red novae flash brightly and then fade, leaving only subtle traces. The impossible appears because we have only just begun to capture it. Astronomers have always worked within limits. Early telescopes revealed stars and nebulae, but the night sky was largely mysterious. Light is finite and space is vast. Even now, instruments like the James Webb Space Telescope, the Vera Rubin Observatory, and next-generation radio arrays are pushing those limits. But they still see only a fraction of what is out there. James Webb peers into the infrared, uncovering objects hidden behind dust clouds or billions of light-years away. It can detect the heat of planetary remnants made of diamond, or the faint glow of early galaxies hosting supermassive black holes. Rubin monitors millions of stars and galaxies, capturing sudden changes in brightness across a wide field, revealing transients like blue stragglers or luminous red novae. Radio arrays like CHIME or ASCAP detect millisecond bursts of radio energy from fast radio bursts, some coming from magnetars, some from completely unknown sources. Even with these instruments, limitations remain. Rogue black holes are invisible except when they bend light from background stars. Oumuamua was detected only because it passed relatively close to Earth and happened to be aligned with a survey telescope's field of view. Objects in the early universe are dim and red-shifted, their light stretched across billions of years, meaning only the brightest or most massive are detectable. Some phenomena occur on timescales too short to catch. Fast radio bursts flash and vanish in milliseconds. Others are too faint, like small interstellar visitors or planetary remnants orbiting distant pulsars. The universe contains countless events and objects that remain completely unseen simply because our instruments cannot yet capture them. Observation is also limited by the areas of the sky that can be monitored. Ground-based telescopes are constrained by weather, daylight, and the curvature of the Earth. Space telescopes are constrained by fuel, orbit, and operational lifespan. Even a telescope like Webb cannot observe all of the sky at once. Astronomers must prioritize targets, choosing where to point, how long to observe, and what filters to use. This creates natural gaps in data. Some impossible discoveries are simply the result of luck, objects appearing in the right place at the right time, briefly crossing a telescope's line of sight. The sky is not static, and our view is incomplete. Even when phenomena are detected, their faintness or brevity can obscure interpretation. Fast radio bursts produce immense energy in milliseconds, but without simultaneous observations in multiple wavelengths, their origin can remain uncertain. Magnetar flares release energy that can alter Earth's atmosphere from thousands of light years away. But unless they occur while satellites or telescopes are observing, scientists might miss the connection. Luminous red novae erupt, then fade, leaving only subtle spectral clues to their origin. The universe exploits these observational gaps, creating events that appear impossible until captured, measured, and analyzed. Bias in theoretical modeling. Even when observations exist, they are interpreted through the lens of theory. Theoretical models are essential. They allow scientists to predict behavior, understand interactions, and plan experiments. But these models are built on assumptions, simplifications, and previous observations. They are approximations of a reality far more complex than our equations can fully capture. When the universe violates a model, what is impossible in theory becomes possible in reality. Magnetars are a prime example. Traditional stellar models suggested that neutron stars should have magnetic fields strong enough to survive, but not trillions of times stronger than Earth. Observations of starquakes and gamma-ray flares revealed that matter under extreme magnetism behaves in ways no model had predicted. The structure of atoms themselves is distorted, and crusts of neutron stars crack in ways not included in previous simulations. Models had to be rewritten, not because the physics changed, but because the universe exploited a regime that models had ignored. Fast radio bursts challenged theoretical assumptions in a similar way. Energy release on millisecond scales, sometimes repeated, sometimes singular, was not predicted. Models of neutron stars, magnetars, and interstellar plasma had to adapt. Some bursts are linked to magnetars, others are not, meaning multiple mechanisms must exist. The universe forces theory to expand, creating categories that didn't exist before. Blue stragglers also violated models of stellar aging. Stars that appear younger than their neighbors in globular clusters required explanations like mass transfer or stellar mergers, phenomena not fully accounted for in earlier stellar evolution models. The biases in modeling extend to scale and scope. Cosmology relies on assumptions about uniformity, dark matter distribution, and galaxy formation. Discoveries like the great attractor, cosmic voids, and supermassive black holes in the early universe appear to break these assumptions. The universe produces conditions at the edges of models, massive gravitational anomalies, empty regions too large for standard theories, and black holes too big to have formed in the time allowed after the Big Bang. Models are powerful tools, but they can fail when confronted with extreme edge cases that the universe produces naturally. Sometimes, models are limited by the resolution of observations. Before instruments like Rubin and Webb, faint or distant objects were invisible, and models were based on incomplete data. Once the objects were observed, they contradicted predictions. The universe had been operating within the margins of observational blind spots, creating phenomena that appeared impossible until finally revealed. Each discovery forces a reassessment of assumptions, corrections to simulations, and sometimes entirely new frameworks. The universe thrives on extremes. It produces objects and events that push physics to its limits. Rogue black holes drift silently, unseen, until gravity exposes them. Magnetars generate magnetic fields that distort matter on atomic scales. Fast radio bursts release unimaginable energy in fractions of a second. Supermassive black holes in the early universe grow faster than expected. Luminous red novae erupt where models predicted calm. Planetary remnants survive the death of stars, remaining intact as crystalline cores of diamond. These are not rare accidents, they are edge cases that reveal the universe's creativity. The laws of physics still apply, but they are tested under conditions far beyond normal experience. Extreme density, magnetic fields, gravity, and temperature push matter into behaviors that are difficult to predict. The impossible appears because our models were never meant to handle these extremes, and our observations were never comprehensive enough to anticipate them. Interstellar visitors like Oumuamua illustrate this perfectly. Its acceleration and unusual shape challenged expectations. No known mechanism fully explained its motion, leading to debates in peer-reviewed journals about hydrogen ice, nitrogen ice, or exotic outgassing. It forced astronomers to consider processes and materials outside the familiar, demonstrating that the universe does not prioritize human intuition or expectation. Edge cases also appear in the large-scale structure of the cosmos. Cosmic voids, massive regions of emptiness, stretch farther than models suggest. The great attractor exerts gravitational pull across thousands of galaxies, yet remains partially hidden behind the Milky Way. These anomalies exploit the gaps in human observation and theoretical prediction, revealing structures that are invisible until the right instruments detect them. Telescopes like James Webb, Vera Rubin, and next-generation radio arrays are designed to confront these edge cases. Webb captures faint infrared light from objects billions of light-years away, revealing early galaxies, planetary remnants, and dust-shrouded phenomena. Rubin continuously monitors vast portions of the sky, capturing transient events that would otherwise vanish unnoticed. Radio arrays detect bursts of energy lasting milliseconds, pinpointing their origin and revealing their environments. By combining these tools, astronomers can confront the universe at its extremes, detecting phenomena that previously seemed impossible. Edge cases reveal the universe's creativity. It creates conditions so extreme they test every assumption. It produces objects that survive where destruction was expected, releases energy where it should be impossible, and moves faster than anticipated. The impossible exists not because physics is broken, but because our observation and understanding are incomplete. Every impossible discovery is a reminder that the universe operates on its own terms, exploiting the full range of physical laws and producing objects and events at the edge of human comprehension. In this way, impossible keeps appearing in peer-reviewed science. It is a natural consequence of observation limits, theoretical biases, and the universe's tendency to produce extreme edge cases. Rogue black holes, fast radio bursts, magnetars, luminous red novae, diamond planets, and cosmic voids are not errors. They are signals, evidence of a cosmos that is stranger, more dynamic, and more extreme than any model could anticipate. Science advances by encountering these impossibilities, testing, observing, and adjusting, each discovery revealing new edges of the universe and reminding us that even the impossible can be real.